All right. Hello, everybody. We'll wait just a minute here to let some folks trickle in. Um, Happy to see some familiar names on the side of the screen. Aisha, good morning.
Hey, how's it going?
Good. I went determined sweatshirt today, but we'll see. It's warming. It's warming in San Francisco today, so
Oh no, I didn't check the weather. That's a good call though. Determined gear.
that's it. Okay. Well, let's get started. I see some folks trickling in. So, welcome everybody to day two of ML at Scale 2023. Thanks to everybody that joined our sessions yesterday to make day one really incredibly impactful. For anybody that wasn't able to attend yesterday's sessions, you can actually watch the replay from each and every talk directly from this page. All you have to do is click on the replay button in the left-hand toolbar down on the bottom. But maybe wait until today's talks have concluded to go ahead and watch those replays. So for those of you that I haven't met yet, my name is Alex Putnam from the Determined AI open source community team, together with Isha and Hayden that you met yesterday, and Kevin as well. So we're really excited to keep the momentum going into today's ML at Scale sessions. So today, I feel like today we're really going to test the limits of scale. Our speakers today are going to show you a little bit of everything. So we have open source transfer learning workflow that you can actually get started with today, concluding Isha's talk. We'll have a full length object detection demo, scaling distributed training and hyperparameter search. We'll be going way beyond ChatGPT-4 today, using your own data and making AI for your domain specific use case. We'll also explore a little bit about responsibility in AI and why transparency and trust truly matters when building large AI implementations. So our speakers are ready and set to go for another great day of ML at Scale content. Remember to be sure to utilize the chat function on the right-hand side of your screen. There's event chat and then there's session chat. So depending on who you'd like to address, just make sure you're toggling session if it's for your presenters. You can also use the Q&A function that's listed right there as well. So with that, I will hand the reins over to Isha, ML developer advocate at Determined. Go ahead, Isha.
Thanks so much, Alex. Let me go ahead and share my screen. Let me actually just vote in the poll too so I can see the responses. Okay, awesome. Opening my share menu. Okay. Is everybody able to see my presentation? I'm going to assume yes. I just can't see Hopin.
Yep, we're good.
Yep. Okay, cool. Just wanted to make sure. All right. Thanks so much, Alex. Hey, everyone. My name is Isha. I'm a machine learning developer advocate here at Determined AI. I'm really excited to be kicking off day two of ML at Scale for you all. Just a little bit of background about myself. I have a background in computer vision. I did some computer vision research in undergrad. Before joining Determined, I worked on adversarial AI, also within the computer vision domain at a federally funded research lab. And I have been at Determined for exactly 1 year now. Yesterday was my 1 year anniversary. So yeah, super excited. Today I'm going to be talking about a transfer learning use case and made easy with Determined. So for anybody who hasn't used Determined before, this is a perfect talk for you. I'm going to be covering all of the intro level concepts in Determined and going to be walking through basically using one of our high level APIs, which is the best way to get started with Determined if you haven't used it before. I'm also just going to be covering a few intro level computer vision concepts, for example, transfer learning. So with that, I'll go ahead and get started. So it seemed like from the poll, some of you are very familiar with transfer learning. Some of you have heard of it before but haven't used it. I just wanted to give an analogy to describe what it is. So for the life of me, I couldn't find a picture of me snowboarding, but I used to love to snowboard. We're just going to pretend that the left picture has a snowboard in it instead of skis on the bottom. But essentially, I know how to snowboard, and last year I wanted to learn how to longboard. And this is a great analogy for transfer learning because the movements involved in both snowboarding and longboarding are essentially the same. You have a stance, it can be either regular or goofy, and you kind of propel yourself forward in the same way. And because I'm already familiar with snowboarding, it was not that hard for me to learn longboarding. So that is transfer learning in a nutshell. That guy in front of me is my little brother. So moving this to talk about models. So transfer learning is essentially the use of a model trained on one task for another task. And this is not specific to computer vision. Obviously, you can do transfer learning in the NLP domain, in other ML domains, but I'm just going to be talking about computer vision specifically. So let's say you have a convolutional neural network and you train it on a generic data set, for example, ImageNet. So the data set that you see on the left here is ImageNet. ImageNet has a ton of different categories. These are just random objects. So like, for example, candle, racket, like these are everyday objects that you can see. And when you train a convolutional neural network on a generic data set like this, it learns low-level features at the lower levels of the neural network. So in the first layers, you'll be able to detect things like lines, corners, edges. And the whole idea behind transfer learning is that if you pre-train a neural network on a generic data set like this, those low-level features will be useful for you, even if you're training your model, you're fine-tuning a model on a target data set. And even if that target data set is like, for example, microscope slides like you see on the right here. Those same lines, corners, edges are going to be transferable features that will be useful for your model to know. So you basically don't have to start from scratch. And if you're a machine learning engineer, you're probably doing transfer learning on a daily basis. I think there's very few cases in which you actually have to train a model completely from scratch. So that is transfer learning. So what is an example of transfer learning in the wild? There's a whole field called digital pathology. I touched on this with the microscope slides, but essentially digital pathology is when you have a microscope slide and you digitize it, so then you make it into an image, and then you analyze it using any computational technique, like for example, computer vision. So let's say like a doctor wants to train a model to aid them in classifying like colon cancer, for example. So they want to know whether a microscope slide has pathological tissue or is just benign tissue. They can utilize transfer learning for this purpose. So today I'm going to walk through an example using MedMNIST v2, which is a large-scale, lightweight benchmark for 2D and 3D biomedical image classification. So there's 18 different data sets. 12 of them are 2D image classification data sets, and 6 of them are 3D data sets. And these are not necessarily intended for clinical use, but it's really good in terms of research. And most of them are basically they basically have different classes, and it's for a computer vision classification. They're intended for computer vision classification. So we're going to just be focusing on one of the data sets from this today. It's called PathMNIST, and the data modality is colon pathology. So there's 100,000 different non-overlapping images here, and these consist of different classes. Some of them are adipose background, like basically non-cancerous tissue, and then you also have cancer-associated stroma. Some other ones. I'm not a doctor, so I'm not actually sure which ones are the malignant versus benign, but essentially the idea is you want to be able to classify these. These were originally a lot bigger than 28 by 28, but then they got standardized down to 28 by 28 to be in like the MedMNIST style. And these were actually pulled from real human tissue. And the reason that I chose this data set is also because the researchers provided a sample training script in PyTorch using scikit-learn and Keras. They have 3 different ones. And it's a great way to showcase why determined is actually useful. So let's go ahead and take a look at this example. All right, I'm going to also check the poll. Okay, great. So a lot of people haven't used determine either. Okay, great. So now we're just going to go through this sample code. Hopefully it's big enough for everyone to see. This is the sample code that was provided along with the data set. So essentially this is a standard training script. Let's go through it starting from the bottom. So first we take in a bunch of arguments using argparse. I'm sure all of you are familiar. Like for example, the batch size, whether or not to convert the images to RGB, whether to resize them, take in the model flag. Then you pull all these arguments in and then pass them to a main function. Let's take a look at that main function. So we're defining things here like the learning rate and the gamma. You can already kind of tell that there's no hyperparameter search built in here because we're hard coding these values. But we're defining our data class. We're doing a little bit of manipulation to set up a GPU. And then we're doing a lot of data prep, establishing our data loaders in PyTorch. We're switching between either a ResNet 18 model or a ResNet 50 model. And then we're doing a lot of like metric logging, so a lot of accuracy calculations, and then we're eventually, I guess, creating lists and going to write them to a summary writer. So summary writer is an object from a library called TensorBoard X. So this is just one way to visualize your results or track your progress during model training. And then we finally have our training loop, and still a lot more metric logging, accuracy calculations. Basically, you can kind of see that this is a very researchy script. It's not very clean. This is what a researcher would probably develop if they're not a software engineer, not a data scientist. More metric logging, yeah, and then we finally had our train function, our test function. So this is a perfectly fine training script. It trains a model on a GPU. It doesn't do hyperparameter search, but it gets the job done. So going back to the slides. So what are the problems with the script? So we saw that there's no hyperparameter search, there's no distributed training. There was a lot of configuration of porting models and inputs to GPUs, but that was only to get the model to be trained on one GPU. We haven't even gotten into how to distribute training across multiple GPUs. There was no checkpointing. I'm not sure if you noticed, but there was, like, at the very end of the training loop, there was a model.save, but there was no checkpointing necessarily throughout the training script. The researchers chose to use TensorBoard X to visualize their training, but that's depending on who you're working with, that you could have different choices in which visualization tools to use. So that's why there's kind of a difficulty with visualizing your training progress. And PyTorch and Keras and scikit-learn, none of these tools offer built-in collaboration features. So if you're working on a team, there's really no way to share your experiment results with your colleague other than just kind of like submitting your experiment, noting down what the results were, and then sharing them. So those are the problems. And I think this is a great segue into why is determine necessary. So the whole reason why determine was born in the first place is that traditional tools are built for the software engineer, not the data scientist, as you can see here. And I went and added a third bubble here for researchers, because as you can see, sometimes these researchers are doctors. They could be like MD, PhDs, for example, and not necessarily even have a background in data science. So there's kind of a gap here between somebody who needs to train a model for like a purpose that's outside of the domain of traditional software engineering, and you need special tools to be able to do that. So go ahead and check the poll again. See what the percentage of users. All right, so a couple people have heard of determine but not used it. So what I'm going to go through now is how would that exact same training script look if you were using determined, and it's going to be the exact same script but just ported to determined. So determined has high-level APIs and a low-level API. Most people, when they're getting started with determined, they'll use one of our high-level APIs. And the whole philosophy behind the trial API let's go over here to the porting tutorial. It's a little bit easier to see when the functions are not filled out, is you essentially run a forward pass and a backward pass on your model in the train batch function and define the same thing in your evaluate batch function, but you don't have a for loop. So essentially determine takes over the for loop and is able to run hyperparameter search distributed training out of the box for you by taking away that control. You also establish your data loaders in these two functions, build training data loader and build validation data loader. And this cuts down the amount of code that you have to write and enables all those features essentially. So taking a look at the same script and how it looks in determined. So these are all the same things. We still establish our number of channels, number of classes, the same model. We just wrap that model with a determined context. We still have an optimizer, but you'll notice that before the learning rate was hard-coded. Now the learning rate can be dynamically set using a configuration file. We still have our optimizer. We still have our scheduler, and all of this is defined in the initialization. And then we essentially build our training data loader and we return a PyTorch data loader. Same for the validation data loader. And then in train batch, this is essentially whatever was in your for loop for training your model. You extract the part inside the for loop and just put it in train batch. So no for loop, but we're giving our model the inputs, taking the outputs, and then stepping our optimizer. And then same thing for evaluate batch, we're passing our inputs to our model, getting the outputs, and then calculating the softmax and our losses. So this is what the script would look like in determined. And just taking a look at the number of lines of code here, this is 148 lines of code. And if we take a look back at the original script, this is like 300 lines of code. So determined literally cuts the number of code that you have to write in half roughly as a heuristic. So that's one thing that you need when you are using determined to run a training script. The other thing that you need is a configuration file. So I mentioned that you can dynamically set the hyperparameters when using determined. You define them in the configuration file. So here's an example of that. Here's some hyperparameters that we defined. Learning rate is still or set to 1. We have our weight decay, for example. You can even set it to like base 10. So we're going from 10 to the -4 to 10 to the -1 as our search space. And then we have a couple other hyperparameters here. And I'm sure you all have heard of grid and random search, but it would be even better if you could use a state-of-the-art hyperparameter search algorithm, for example, adaptive ASHA. So that's a built-in thing that you can use. All you have to do is set adaptive ASHA here as the name of your searcher. And then how it works is the way you connect your configuration file to your actual training script is you specify the name of your Python file here and then the name of your trial class. And in our case, it's my MedMNIST trial. And there's a few other things you define in the configuration file, like for example, the name of your experiment. And the way that you submit an experiment is you make sure that your determined master is set to the right variable. Your determined master can be anything. So it can be your laptop, it can be an AWS instance. For example, this is the IP address of the current AWS cluster that I'm using. And then you can submit an experiment by running .experiment create, passing the configuration file, and then passing the directory where your model code is also located. That works. And that's how you submit an experiment to the master. So going to the web UI now, that's where your experiment will then show up. Let's take a look at an experiment that has already run. So this is the same exact experiment. Here's the hyperparameter search in action. You can also see a list of all of your trials and the validation metrics, duration of the trials, and the code that you submitted, and the actual submitted configuration as well. So determine kind of solves all of the problems that we talked about earlier. So now you can do hyperparameter search. Distributed training is super simple. For distributed training, you essentially set the number of slots that you want to distribute training against in your config file. You can also now very easily collaborate, because if all of your colleagues have access to the same cluster, they can just go in, click on an experiment, see the code configuration that you submitted. Yeah, so at this point, I'll pause for any questions. Go back to the chat. Great, we have a lot of researchers, data scientists here. Awesome. So that covers the training portion. Let's also take a look at inference. So until now, there was also, so this covered training. A lot of people also want to do inference, so basically model evaluation, but also as a determined experiment. And until now, there was no dedicated way to run inference as a determined experiment. So what we needed was something like a batch processing API, where you can batch process anything, for example, like a held out test set. There's also other things you can do with the batch processing API, like generate embeddings, for example, in a retrieval augmented generation situation. But what I wanted to do was evaluate my model that on the held out MNIST test data set and submit an experiment like so, like using det create, but with the inference configuration file. So let's go through the code for that. So the batch processing API works exactly the same way as the trial APIs. You still have a Torch batch processor class that you need to create a subclass of, and you define all of the things you need to define in the initialization. So the first thing is our model, but instead of defining optimizer, learning rates, things like that, we just download a trained model checkpoint from the relevant determined experiment. So here I'm downloading a checkpoint, and that's our trained model. You can also add in your softmax here. And the way that the batch processing API works is that it distributes whatever load it is that you want to batch process across multiple ranks. So in our case, since we're calculating accuracy across a held out test data set, we need a metric reducer so that we can then aggregate all of the metrics at the end of this and then report one final accuracy. So that's why I also have this accuracy metric reducer, and this cross-slot reduce function is what's used at the very end of the inference experiment. And then you also have this process batch function, which defines exactly what you want to do in your process batch. And in our case, it is just evaluating the model. So we give the model our inputs, get the outputs, evaluate the accuracy score, and then update the reducer. And then in our main function, we essentially just establish our data set. And you call Torch batch process, pass in the MyProcessor class that you created, and then pass in the data set. And this data set can either be a PyTorch data set or it can be a Hugging Face data set. And you can also just create an experiment the exact same way, but then pass in your inference config file. Within the inference config file, it's pretty much the same thing as when using a trial API. So you have an entry point, you specify your Python script, you have a name for your experiment, you can still have hyperparameters that you can access, and you still distribute it across multiple slots per trial. So let's go ahead and take a look at that experiment in action. Yeah, so that experiment is currently queued. And you can take a look at the finished experiment here. So you can see that the average accuracy across the held out test set was 88.7%. So that is the batch processing API. Yeah, so basically now we have the full workflow from training and evaluation. Any questions at this point?
So Isha, yesterday Corey gave a talk. During Corey's talk, he was talking about batch inferencing using Core API and using Hugging Face and DeepSpeed. I wondered, what are the different scenarios that you would use the Core API and then this new batch processing API, or is that are they similar use cases, and kind of how does that work?
Yeah, so you could definitely use the core API for batch processing. I think this is more of like a dedicated batch processing API, so it's easier to use. So there's a lot of things you can do with the core API. The core API is super low level. It's essentially for doing training in Determined, but if you don't necessarily want to enable everything out of the box and lose control of your training loop, like for everyone who's not familiar with the core API, you can enable things separately. Like you can do just distributed training with Determined, but you don't necessarily have to enable your experiment to show up in the web UI. You can technically write an inference script with batch processing and then port it to Determined using the core API, but it's very low level. It's for people who really want fine-grained control. I think the batch processing API is it's like kind of halfway between the core API and the trial APIs in that it works the same way as a trial API, but it does give you enough control that you can do more than just evaluation with it. Like you can also compute embeddings. So it's kind of like, what are you looking for in terms of how much control do you want and what functionality do you want, if that makes sense. Any other questions? Oh, Q&A, I didn't see that. What is the level of support you can get to help porting the code to use Determined? If you mean in terms of like tech support, we have our community Slack channel, so you can, if you can ask any questions that you have there. Either myself or one of our engineers will definitely jump in really quick to help you with that. Okay, cool. So we basically covered training and inference. If you wanted to serve your model, you could very easily do that. This is not the best visualization, but essentially what I did was I created a Flask server using a train checkpoint, and I passed it this held out image from the test data set. This is a picture of adipose tissues. So you can see that this is the correct prediction, and this is using the train model. You can use any serving tool that you like. This is just one example, but the point here is that Determined essentially provides the functionality to train and evaluate your model, and then we're open source. We're compatible with any serving tool that you prefer. So just to recap everything that I covered, Determined sits in the middle here between data acquisition and preparation and model deployment and inference, and we provide all of the things that you see in purple. So we do cluster sharing and resource management. We do distributed training, hyperparameter search, visualization debugging, batch inference, experiment tracking. We're framework agnostic. So going back to the original case where the researchers who developed MedMnist had different scripts that you could use to do the same thing, like using PyTorch versus Keras versus scikit-learn. We're framework agnostic, and you can still collaborate with your colleagues. Next you'll hear a talk from Jimmy, so he'll talk a little bit about Pachyderm. You can use any tool for your data prep and any tool for your model deployment. So that basically covers what I wanted to present today. If you haven't joined our community Slack, here's a QR code to make it easier for you to jump in, and that's a link to our homepage. If you have any questions for me specifically, here's my email. You can contact me at firstname.lastname@hpe.com, and then you can also contact me via Twitter. My handle is Isha Bites. But yeah, I'll stick around for any more questions. And I will stop sharing my screen so it doesn't echo as much.
Thanks so much, Isha. Thanks for kicking day 2 off. So for those that want to ask Isha any questions, she'll remain on this session. Otherwise, we'll switch over to our next talk by clicking sessions on the left-hand side, and that'll be from Chief Scientist at Pachyderm, Jimmy Whitaker. So thanks again, Isha. See you in a little bit.
Thanks, Alex.
All right. Good afternoon, Jimmy. Good to see you.
Hey, how's it going?
Pretty good. All right. I'll hand you the keys. Go for it.
All righty. Let me make sure I share the right thing. I think we're in business. And yeah, well, hello. Welcome, everybody. I'm Jimmy Whitaker. And today we're going to be talking about the reproducibility crisis in machine learning. So first, I'll start by introducing myself. I'm Jimmy Whitaker. I'm the chief scientist in the AI and strategy group at HPE. I was brought on by their recent acquisition of Pachyderm. So I've actually been deeply involved in just the world of machine learning and AI for, a decade plus now. And basically, my main passion is just, it's kind of pragmatic. It's building things that work. And so I started as a research engineer. I've built a lot of NLP and speech recognition applications and models for financial institutions, and then moved on to kind of managing and directing applied research teams. And more or less what I've found in that time is that a lot of the time I would have liked to be spending on solving machine learning problems like tuning the model or tweaking the data set, or even just evaluating the edge cases and really just making these models super practical. I've ended up spending on just on getting tooling to work, or just getting my tooling to give me consistent results. And so the topic that we have today is very much at the heart of what I've wanted to solve, or it's very much the heart of the issue that I've run into, and that's from crisis to clarity, ensuring reproducibility for AI. So we're going to talk about the issues that increasingly are just casting a shadow on the promise of machine learning and artificial intelligence, and in particular, the reproducibility crisis. So what the reproducibility crisis is, and then the main thing that we're going to focus on is not on demos, but on giving insight into kind of the fundamental principles for building a machine learning organization that's ready to solve any type of machine learning problem. And so with a weighty introduction, we'll move on to looking at our agenda. So first, we're going to start by understanding the nature of what I mean by a crisis. So what is the reproducibility crisis? What's at stake? And also what's at stake if it's not addressed? So this is more than just like a technical hiccup, but it touches at the heart of what AI is supposed to be. It's supposed to be a dependable and trustworthy set of tools that enable us to make better decisions and automate complex tasks. And we're seeing that more and more with agents and all kinds of other things. So after we spend some time focusing on understanding the crisis, we want to move on to how do we confront this crisis. So we're going to explore a kind of a variety of strategies and principles that help us not only combat reproducibility or ensuring reproducibility in the systems that we're building, but we also want to learn from experiences that kind of are tried and true techniques in software development, in particular the shift to DevOps, and explore ways in which we can start building more reliable and transparency into our AI systems to avoid these pitfalls. So this brings us to the next item here, which is going to be how we at HPE are actively trying to solve this with our AI at Scale platform. We're going to discuss how the right platform can serve as a really strong foundation for more reliable and scalable AI applications. And in particular, we're going to focus on two key pieces of the platform, the data management side and the model training side, or MLDE, machine learning data environment, and the machine learning data management here. And we'll talk about how these two pieces kind of come together. And then finally, we're going to wrap up with just a conclusion, a bit of a summary. So with all that, let's get started. So reproducibility and transparency in AI. So we're living in a time when AI is becoming just increasingly pervasive in our lives. So from the recommendations that we get on our favorite streaming services to voice assistants on your phone, all of these different things that can help us just navigate our day, AI is everywhere. And while it can bring about a lot of benefits, it also brings a lot of challenges with it as well. So the reproducibility crisis is one of those challenges, especially in making AI work for what we want to do. And there are two parts to this crisis. So, and the two pieces that we're really going to talk about today are reproducibility and transparency. And these can be kind of confusing. They can sort of be conflated together. So I want to spend a little bit of time kind of teasing out the differences between reproducibility and transparency, and also why we're including transparency here as well. So Reproducibility, kind of simply put, is about getting consistent results from your AI system. So if you ask your AI system the same question twice, it should ideally give you the same answer each time, assuming you don't have it baked in some temperature and stuff like that. There's plenty of edge cases, but in general, if you ask it the same question, it should give you the same answer. Transparency, on the other hand, is about understanding how your AI system arrived at that answer. So for instance, imagine you're a business owner and you're using an AI system to make some decisions. If your AI system isn't reproducible, it's like having an advisor that gives you different advice every time you ask the same question. And so that can be really frustrating, especially if you're asking the same question and they're giving you different pieces of advice. You don't know how well you can trust that. So it's really not useful at all. Transparency, on the other hand, is about understanding how you arrived at this answer. So in that case, it's like having an advisor that just says, trust me, without explaining their reasoning. And this wouldn't fly at any reputable organization. But basically, without reproducibility, we're risking making inconsistent decisions based on because our outputs are changing every time. And without transparency, we're risking blind faith in the outputs we don't understand. So in either case, we're losing trust in the very systems that are supposed to help us, and that's kind of the key thing. We're trying to build systems that we can trust. They're reproducible. We know that they're going to give us that same result. They're going to give us that reliable result every time. If you had a calculator that gave you a different result every single time you punched in a problem, you wouldn't really trust that calculator very much. And transparency, how you got at that answer. If someone couldn't explain the steps and what changed and why there's a different answer now, then that's a problem as well. So some might ask why we're incorporating transparency in here as well, instead of exclusively talking about reproducibility. And the main reason is transparency is here because perfect reproducibility, so reproducibility, not just reproducibility, but perfect reproducibility isn't always achievable, as we're going to see later on. And in these cases, transparency becomes more important to reduce the overall risk of the system. So overall, just the stakes in machine learning and AI, especially when we're building systems, the stakes are really high. The cost of misinformed decisions can be substantial. So whether we are facing, obviously financial losses, or damaged reputations, or even in extreme cases, businesses can face regulatory sanctions or many other things. So when we talk about this being a crisis, it's not just about algorithms and data. It's about building trustworthy, accountable systems, and also the very way that we do business just in the era of AI itself. And so with all that said, it's really crucial that we tackle this crisis head on. So I just want to dive very quickly into kind of a practical scenario here, just to put a little bit of meat on the bones of kind of this reproducibility and transparency kind of trade-off, if you will, or how these things work together, actually. So let's take a look or just kind of think about AI and the use of facial recognition, just to highlight the significance of these two components. So in most, I would say, facial recognition applications today, you're likely using something like a convolutional neural network. And so this is commonly used for facial recognition because they're just incredibly powerful. But the problem is they often act as black boxes. The decision-making process can be like really opaque, especially if you have millions and millions of parameters or many layers of abstraction to get you to that end goal. So because of this, the big concern, at least in the decision-making process, is that process is opaque, and this can lead to challenges with if those decisions are reflecting bias. So, for instance, incorrect or biased identifications won't only erode the confidence of the system, but it can also result in regulatory repercussions, especially in the case of facial recognition. So, for instance, while we might be able to choose a simpler, more interpretable model, the performance might be compromised at the same time. So in transparency, we may be able to document the environment that we're using or share the model weights and make everything really transparent as to how we got to this end result, or detailing out the methodology and documentation. And that's a huge step in the right direction. On the reproducibility side, while it can be really challenging, it's not necessarily unattainable to achieve a high level of reproducibility in the process. So for instance, we can use fixed initialization values and seeds, deterministic algorithms, version control for our data, and even just validation on multiple hardware options, just so we know that we're getting the correct result and that our result is going to not only work in our training environment, but also our production environment. But there's a lot of different ways that we can incorporate reproducibility. But at the end of the day, like convolutional neural networks are still a little bit black boxes. And so this is why reproducibility is achievable, but it's not always optimal. Because, for instance, in the deterministic algorithm case, there's a performance cost as well as that is kind of the trade-off to getting that full reproducibility. So I've alluded to this already, but I just want to kind of key in, and I'm not going to read everything on this slide, but just wanted to talk about kind of the cost of neglecting reproducibility and transparency. And there's some pretty substantial implications, and some of them may not be immediately obvious. So first is that it undermines the trust in our AI systems, which is essentially what's needed for widespread adoption and even just effective decision-making. So for instance, if our outcomes can't be trusted or understood, then stakeholders may be reluctant to even rely on our AI outputs. It may lead to missed opportunities for innovation or efficiency or all kinds of other things. Another thing is that it fosters just the propagation of bias or incorrect results. So for instance, like in our facial recognition model, if we have only trained on certain subsets of the population and maybe don't have full representation for certain races, then our models can be biased in certain scenarios. And that can lead to some massive regulatory or even just legal risks with regards to that, not only just a bad experience or reputational damage. But basically in a worst case scenario, our biased AI could lead to unfair practices or even just harm individuals. For instance, another one there could be in the case of autonomous vehicles, where there's even the potential for loss of life if AI goes wrong. And so being able to fix issues as we find them and having reproducibility and transparency allows us to dig deeper into those things. Lastly, and this is the one I've probably experienced the most, is it's potentially a huge waste of resources. So without reproducibility, researchers can kind of unknowingly base their work on flawed studies or models, leading to wasted time, or even trying to reproduce old work that's already been done, but there wasn't transparency in how it was done, or consistency in where things were put, or even just an organizational kind of paradigm with which to approach these problems. And so kind of in sum, neglecting reproducibility and transparency not only compromises just the risk of the overall system, but even just the integrity, the utility, or even the ethical application of AI. So we talked a lot about some of the difficult things, or the importance really of the reproducibility crisis, but now let's shift over to how we actually confront this crisis. So in order to navigate kind of the complex landscape of reproducibility and transparency and AI and data and all these things are moving, I find it's really beneficial to draw parallels from another field that has successfully managed to streamline a process that's maybe somewhat similar, that's improved the efficiency and the reliability of a system, and then learn from that and try to apply it to machine learning and think about how things are different, but just look at the fundamental principles that they've used. And in this case, I find that the world of DevOps is a really interesting kind of case study for this. So now you may wonder what this has to do with machine learning. And as we go deeper into this section, we're going to draw some parallels between this. But if you're not familiar with DevOps, at a high level, DevOps is really a combination. The word itself is development and operations. And so DevOps. And it refers to a set of practices that emphasizes collaboration between software developers and engineers and other kind of IT professionals to deliver the software more reliably. And this has been really kind of revolutionary in the culture of creating an environment where developing, testing, and releasing software happens on a fast cadence and has led to a lot of amazing developments on both the development of web applications and all kinds of other areas just in software in general. And there were some key developments here. So this didn't just happen overnight. There were the waterfall approaches in the past where you'd spend huge, long, lengthy planning cycles trying to figure out what your software architecture should look like, and then going off and building that, kind of like how you would build a bridge. But with software, you can iterate really, really quickly if you have the right tools in place and the right abstractions in place. And so some of the key developments were version control and continuous integration, continuous deployment, CI/CD, some agile software development and practices there. And even when your system is put into production, you have this continuous monitoring and consistent way to deploy that system. So like infrastructure as code, so you can automate this stuff. But really the core was by having version control and focusing on testing and releasing and iterating on things quickly, you can move a lot faster. And not only that, you can move a lot more reliably as well. But so basically, much like software development about a decade ago, machine learning today needs its own kind of DevOps. And a lot of people are familiar with MLOps and these other kinds of things. And I think that starts to slot in here. But basically a set of best practices that can guide data scientists and machine learning engineers to work effectively together to create models that are not just high performing, but reliable and understandable, where we have reproducibility and transparency into the entire process. But the problem with this is what is different. So software development, it's very similar to DevOps. We can imagine tests and integration tests and even monitoring. But what's different about machine learning, and how do we incorporate these techniques? So the most significant difference when it comes to comparing traditional software engineering with machine learning development is the data. So in machine learning, the data is really, and I can't emphasize this enough, the data is the new source code. It is telling our model what should be learned. But we have machine learning techniques and our model code that's telling our model how to learn, but the data is actually what it is learning from. It is the source code. It is the structures in words, or the structures and images, the relationship of pixels that are actually being learned from. And so in machine learning development, this ends up leading to not just one life cycle that we saw in software development, where you're iterating on your code and then you're producing an end system. But instead, you have two life cycles, and there's a symbiotic relationship between these two. So you have your data life cycle and your code life cycle as well. So the code life cycle, to focus on it first, this is the aspect of machine learning ops that most closely aligns with traditional software development. So it starts with developing your code for your machine learning model, and this is also usually in a collaborative environment. So you're using things like Git or GitHub to store and version your code. You can roll back changes if something was wrong, and you can see how collaboration between members can be really beneficial. And then the next thing is the code. Let me back up a bit. So this kind of happens, and then the code goes through. You're usually testing this code. In the unit test, you then have your integration test to see that this is going to work in production, and then you go ahead and push it to production. And this similar thing happens in the code lifecycle here, where we're going through, we're building our code, we're testing it, we're validating it, assessing its performance, fixing bugs and everything else, and then we're pushing it to production. But in the data lifecycle, this lifecycle is a little bit more unique to machine learning ops. So we have this process of identifying, collecting our data. This involves even just managing the different versions of our data, because data is never stagnant. It's always growing over time. It's always changing as we learn more about the bias that is incorporated into our data sets. We need to alleviate that. So managing data versions and is kind of similar to managing code versions, actually, where we want to track the data and how it's changed and even used in the models. But then there's also this convergence point. So model training, for example, we're combining the code, and that we've iterated on this code again and again with the data, which we've also iterated on again and again. And so the convergence of these two things is really key, a key component, because you have two maybe individually versioned things that are coming together to produce new artifacts, new models, or training objects that we're going to be using for another downstream task. And so managing all of the data lifecycle and the code lifecycle together is kind of crucial for machine learning operations. And both of these life cycles have to work together seamlessly to be able to manage this appropriately. So if we kind of pull back to that image I showed a second ago, machine learning development we can see is a lot more complex. First, we just had the code, and we're unit testing and unit testing that code, and then doing integration tests for pushing that into production, and then doing our system monitoring. Now we have this model training step that's in the middle. So we have our code, which can be unit tested in traditional software development there. We still have integration tests, but this also stretches across our model training environment. And then we have our running system. But the whole while, we have another input. So we have our data that's coming in during our model training, and we need to perform data tests and skew tests and see how it differs from the data that's coming into the running system, and even do some prediction monitoring when our system's deployed. And so this is just massively more complex than the first thing we saw. We added a whole another life cycle, and it's kind of exponential in the way that it relates to the complexity of the problem itself. But what and this is going to look a little overwhelming for a moment, and it's a bit intended to do that. So if we tease out kind of all the interactions, or a lot of the interactions that we see between the code lifecycle, model training, and even the data lifecycle, and then combine those with some of the DevOps principles, or in this case, MLOps principles, then we start to see all the different interactions that can happen and how we need to be thinking about them. We need to be testing, and we need to be versioning, and we need to be thinking about automation and reproducibility across each one of these components, or the interaction of these different systems. So if we really tease out all these interactions, we see that there's quite a few just operational situations that we need to consider. So here there's 7 principles and examples of kind of what we need to be thinking about for each of these life cycles and interactions. But then there's one other component to this as well, and that's scaling the solution. So I realize I'm moving quick, and I'll pause a little bit. There will definitely be some time for chat and Q&A at the end, but I'm just trying to show you how this scales and how the complexity really starts to get out of control. So for instance, if we're trying to scale this solution, so say we have all of these different interactions, these 21 different situations solved, we then need to figure out how to scale that situation. So in the early stages of building machine learning models, we usually, or at least I do, start with a small experiment on a single machine. Infrastructure is relatively simple to manage. There's no real shared resources or data sets that I need to really track. It's just me working on something, and I don't need to think as much about productionizing results. But at this stage, ad hoc experiment tracking is really just me keeping notes and records about what I did and how I obtained the results. And that's typically sufficient for kind of a day one mentality of just me working on a problem. But as we start to scale, we start thinking about those day two complexities, the landscape really starts to change dramatically. So when you start to work with much larger data sets or more complex models, or even a larger team of data scientists and machine learning engineers, all these new requirements start to emerge. So now you have many users accessing and modifying shared resources, from data sets to model parameters. There are various data sources to manage, and the possibility of a mix of technologies, from different machine learning frameworks to cloud resources to on-premise hardware, it really starts to become overwhelming. And this also incorporates the need for systematic experiment tracking. How do you share your results with someone else? It's no longer feasible to rely on just these ad hoc nodes. So overall, once we start looking at the explainability and transparency in AI, or reproducibility and transparency in AI, there's the first part, which is thinking about all the interactions and how we actually apply reproducibility and transparency into that process. And then there's the whole second aspect, which is now how do we scale this process effectively? So in essence, as you move from small scale experiments to a full scale MLOps operation, the complexity just increases significantly. And so, but however, effectively managing this transition is crucial to providing, I guess, a full scale machine learning system. And that brings us to kind of how we're thinking about these things at HPE. So this brings us to the HPE vision for our AI scale platform. So our vision is to build the world's best platform for developing and deploying AI applications at scale. And so this is a lofty, yet, in my opinion, a realistic goal for some of the things that we're, the tools that we've chosen, how we're building things together, how we're trying to pull these different pieces together to build this platform at scale. It's really exciting to me, and kind of probably the biggest reason I'm so excited about what we're doing at HPE for the AI at Scale platform. So when we talk about the features of the AI at Scale platform, there's really kind of 3 components. There's the data management component. There's the what I'll just say is the development environment, or the model training component, which we heard you should talk about in the previous conversation, or sorry, the previous session. And then there's the online inference. So once we have trained our model, we need to put it into production. And so What I have in here is mainly focused on kind of the enterprise versions of these, but we have a heavy open source mentality on this stuff as well. So for instance, in the data management side, Pachyderm, which is where I came from, is a key, is the open source product for that column. Determined AI is obviously for the development environment here. And there's a couple of different options and solutions on the inference side. But the reason I mention that is if you hear me say Pachyderm, I'm really referring to the data management side, or Determined, I'm referring to kind of the model development optimization side. So just mentioning that one, but the enterprise solution is where we're really digging in to make streamline these operations and make sure that they all work kind of nicely together. So as far as the features go, so Pachyderm, or MLDM here, is an open source data platform that provides data versioning, data lineage, and automated pipelines. So there's a lot to go into here. I'll give us a little bit of a high-level view of some of these features. But basically, the data lineage features and the data management capabilities allow you to version and track code in a very similar way as you would, or sorry, track data in a very similar way to which you would track code. So for instance, you can track each piece, each data set from its source through a pipeline, even to the final result, which can also tell you a lot about transparency. So if we apply code to our data set, then we can actually see the artifacts that were produced from that. So we can get into some really interesting things with automated pipelines and just full MLOps processes in that. So the second component in the stack is Determined AI, or the machine learning development environment. And so Determined is an open source deep learning training platform that can handle tasks like hyperparameter tuning or experiment tracking, resource management, all these different things that help you scale up the machine learning development from one user to many. It enables collaboration, all kinds of other things, but you can also share the experiment results and provide a lot of transparency into what you're doing. So we kind of alluded to reproducibility on the data versioning side and everything. We'll dig in a little bit deeper, and also kind of the transparency in all of these components. Finally, we have a Kubernetes-based platform for serving our machine learning models. So while we're talking about scaling, providing a scalable environment for training, we also want to do the same thing for deploying and serving models. So this is an active area where we're working right now, but support for many different frameworks, many different types of rollouts and all kinds of other things is an active area of development, but performing well in a production environment is just as crucial. Once you have a trained model, if you can't put it into production, then it's not so useful. So yes, obviously that's a huge component there, and all of these systems work together. So the first thing I'm going to dive into here is reproducibility in the data lifecycle. So, and this is where Pachyderm, or the HPE MLD machine learning data management component comes in. So the key areas of Pachyderm are really that it is a data versioning, data lineage, and automated pipeline system that's built on top of Kubernetes. And a little bit more detail, the two kind of key components to this are the data management system and the pipeline system. So on the data management system, we can kind of think about it as S3 buckets that have versioning, but they're much, much more complex. There's automatic deduplication of data. There you can store any file type similar to object storage there, but you can version things in repo styles, so Git-like version control semantics. You can have branches and all kinds of other things, all applied to your data system. And there's some really, really interesting things here that I don't have time to go into, but give it a look. There's some cool stuff there. The second component here is the pipeline system. So the pipeline system, so we're built on top of Kubernetes, and what this means is the pipeline system is a computation layer that enables complex data transformations, such as like a directed acyclic graph or of containerized analytics or tasks that pull data from the data management system. So basically you're pulling version data, you're performing some operation on it, and then you're outputting data that can also be versioned. And so this means that not only can we have essentially like data-driven type tasks when our data changes, it can trigger things, but also we have end-to-end reproducibility of everything that happened in the system. We know what data came in, we know what code was run from our containerized tasks, and then we know what data was output. And so this gives us end-to-end reproducibility on the data management side. So this is really cool because on the version data front, so here I have kind of a diagram of a data set, and our data is organized in Git repositories. We can see the different commits that I have here. And this Git-like structure means I can always get back to the version of my data or the piece of data that was incorporated into a particular task that was run. So this means that regardless of whether I'm using models or images or video, I can automatically get back to a reproducible situation where this was my input, this was the code and environment, containerized analytics, and environment that ran, and what was produced from it. Now, this is also kind of neglecting the fact that if you have randomized logic inside your pipeline, then obviously that's a flaw in just the approach to reproducibility there. But as far as getting reproducibility with your data and applying code to it, Pachyderm pipelines or the MLDM pipelines are the way to do that. And this also gives us some really cool things around data-driven pipelines. So I usually say if you squint, this kind of looks like CI/CD or continuous integration, continuous deployment, because what you can set up is whenever my data changes, say I want to retrain a model. So here I have my modeling pipeline on the right side here. And so whenever my data set changes, I want this to automatically kick off a new training job of my model pipeline. So I've labeled some new data, I update my data set, rather than going through the process of manually doing, pulling down that data set, running something locally, and then pushing the model. I can start to automate all that. And I can set up these data set, in this case, a data set trigger or a data trigger to automatically process my data. And there's a bunch of other cool things in there, but you can auto scale and do some parallel processing, and there's support for any type of coding language. So even if it's just a data processing pipeline that uses some old Java code that was used in your organization or something like that, then you can even parallelize that and run that. I've actually used that a lot on the speech recognition side, which is kind of cool. But kind of the key here is this is really how we provide reproducibility and transparency into the data lifecycle. We have version data and we have version pipelines, and then we combine those two together, or when we combine those two together, we also have versioned artifacts that come out. And so this gives us reproducibility in the sense that we know exactly what went into every single run, and also transparency because we know we can look at the underlying data, we can look at the underlying code and see not only what existed when we ran that thing, so the reproducibility, but also how it's changed over time. So the next thing that we're going to talk about is the machine learning development environment. Now, I'm not going to jump into this too heavily because there's been a lot of people that are talking about this during the process of this ML at Scale 2023. But it is important for when we're thinking about how we're doing our model development. And so Isha, again, the talk right before me, talked about a lot of these things, but the MLDE platform, the Determined platform, is specifically designed to kind of tackle the challenges encountered in the machine learning, like that model training, the machine learning model development cycle. And so this provides a lot of capabilities that are just essential for kind of AI at scale. If you're training large models, if you're training models at scale, then you end up thinking about things like hyperparameter search or experiment tracking or distributed training, resource management, and reproducibility and model management. All these things start to come together. And so this is just kind of a quick slide to show how the data, so we talked about how we have this data acquisition and preparation side, which typically happens on the Pachyderm/MLDM side. But then when we get to the MLDE side, we're wanting to train and do something with that. Then we want these other sets of capabilities, and these pair really, really nicely together. So, so yeah, Determined basically helps you manage kind of the whole model training process and kind of access, and not only at an individual level, but also at a scale level. So once you start incorporating the collaboration aspects and everything else, it ends up being a force multiplier for data science teams, especially for managing resources or even just building models faster, which is huge for iteration. So when we talk about reproducibility in the context of MLDE, one of the key things is deterministic model training. So the hard thing about this is deterministic model training is it kind of inherently has some issues because there's in the model training process, especially when you start getting to the GPU level, certain algorithms are better if you just do if you use randomness to do some approximations. But Determined AI addresses this by facilitating deterministic model training, where rerunning the experiment with the same inputs will produce the same or similar models. And so this makes results more predictable and consistent in enhancing this reproducibility. But once we have our models, we want to make sure that we're able to use those models. So a model registry is kind of a key thing. And so this helps us not only track and manage our models for deployment, but also creates an organized system, kind of a single source of truth, where model versions, along with their parameters and performance metrics, can be easily recorded and accessible, which for maintaining models and reproducibility over time is huge. The next thing I have here is experiment and metadata tracking. So every experiment in Determined is automatically run with logging and includes details not only about the data and where the source of the data that was used, the model was trained on or tested on, but also parameters and results and all kinds of other things. So providing this level of transparency kind of gives you the full context of every experiment and also helps you kind of come up to speed on the work that someone else has done so that you can always trace back, kind of walk back and trace the steps that were used to get to that particular result and how it was achieved. And the final thing, and this is a relatively simple thing, is random seed setting. So this is an important feature kind of regardless of any platform, but being able to set the random seed so that you can use randomness, but there's some level of determinism associated with that. And so this further improves kind of the reproducibility of the entire system. So one thing I wanted to dig into a little bit more here is, so while Determined AI can significantly enhance reproducibility, perfect reproducibility not only might not always be achievable, but it might not even be desirable in some situations. So particularly when computation is scaled across multiple devices, this introduces additional randomness. Nevertheless, Determined AI helps get as close as possible to this perfect reproducibility situation. But in the world of deep learning, the pursuit of perfect reproducibility often is just a little bit of a mirage. There's inherent randomness in model training and differences in hardware and software environments, variation in the data that's used for training and testing, and these all contribute to kind of the elusiveness of this pursuit. So, but while this might seem a little bit disheartening at first glance, it's important to remember that absolute perfection or absolute reproducibility, perfect reproducibility, isn't really the goal, but rather striving to have more robust and credible models. This isn't about recreating every single result with exact precision in the case of trying to build these models for particular applications, but rather about minimizing the range of and variance of our issues and our models so that we can maximize just the consistency of building and training and deploying and getting reliable results over time. So by doing so, we're improving the robustness of our models, enhancing the reliability and credibility, even if we're not providing kind of this perfect reproducibility in the process. So yes, so perfect reproducibility is essential for a robust and credible model. So one of the beauties of the platform really is just this AI at scale workflow. It's designed to not just be you click these 4 buttons and this will give you an output for very standard situations, but the beauty lies in the flexibility where you can design it and mold it to your individual process. So a lot of the things we talked about earlier are versioning data or versioning different types of model artifacts, or even kind of, I mean, there's all different kinds of formats I've seen. So like point clouds and all kinds of other things. We're not built for just doing one particular type of model training, like image classification or something like that. But we have the components, and we've seen the components in house. The simple abstractions that are built to scale can be used to simplify, to create a world where you can build whatever you actually need for your particular problem, with the same sets of tools and get the same sets of results. So here we see a very simple example going from our data set to our model deployed, and how this kind of works. So this is more of like a rehash where we start with our data set. We already have data that is being versioned and captured, and the process of cleaning and curating and labeling our data can be captured using Pachyderm. And versioning this data is then fed into the model training aspect, which can happen to determine where we can train our models efficiently. Post-training, we can validate our models and test them against all the different data sets that are also versioned to make sure that they're giving us the performance that we're interested in and are robust. And then finally, we can automate this deployment for inference. So this mentality, or this kind of bigger picture where we can quickly move from iterating on our data, iterating on our model, going back to iterating on our data, moving into the testing, iterating on our testing, going back to iterating on our model, and streamlining the process to deployment. All of these things coming together are what really enable those two life cycles, those two loops that we talked about, that managing the data lifecycle and managing the code lifecycle, and how these two things come together into kind of one set of applications or one platform, which is the AI at Scale platform. And so this has been a really fun process. I wish I could say everything works perfectly and like pull it today. So much of it does, but there are still some things that are difficult in this process. We want to hear about people developing things. We want to work with you on doing some of this stuff. So like reach out to us if you're interested in some of these things. I know I'm constantly thinking about how we can make the curation of data a little bit easier as far as external data coming into Pachyderm and how we iterate with that. When we start model training and pulling data from Pachyderm, that works really, really great. But then model testing can be interesting. Like, am I pulling different data sets, or how are we using these things? Are we just doing a random split? Because that can have some implications in deployment. There's a lot of really cool and interesting ways this is going to evolve over time. So this platform is just the start. There's some really cool things to start with, but it's far from over. We've got a lot more cool things coming up. So with that, I think I'm coming up on time. I think I've been talking for a while. So I'm just going to recap real quick, and then we'll kind of open it up for some Q&A if there is any. So for recap, so let's talk about what we've explored. So AI is becoming pervasive. It's bringing many cool things, but also many complexities to software systems. And that's introducing new risks with the lack of transparency and reproducibility. This lack of transparency and reproducibility can lead to misaligned outputs. It can lead to troubleshooting difficulties, decreased trust, or even regulatory backlash in some of the more extreme cases. But the solution lies in providing tooling that provides versioning and reproducibility and automation and just workflow enhancements and collaboration across the code and data lifecycles. And the key really is having the tooling that's going to make us more efficient, rather than having to think about all these things. There's only so much cognitive load that any human can hang on to during a daily basis. So having tooling allow us to offload that cognitive load to apply ourselves to the important problems is going to be the key there. And finally, the HPE AI at Scale platform is our approach and kind of our push for being able to solve this end-to-end AI lifecycle problem by providing a platform that not only allows you to manage all the complexities, but also scales to the level that you need it for not only enterprise, but just actually how you can iterate and move quickly and even scale the effectiveness and efficiency of server processes as well. And so with that, I just want to say thanks very much. I will have my email and Twitter, Medium stuff there if anybody's interested in that. And yeah, I'll pivot over to some Q&A.
Thanks so much, Jimmy. Hey, are you able to just toggle session and then Q&A over on the right-hand side?
Yes.
With things on the data management side.
Sure. So the first thing I think was, will the presentation be shared? I can definitely share that. I'll probably lean on you, Alex, or some of the others to figure out how best to share that within the Hopin platform. But yeah, I'll figure out how that works. So the second one I see is I don't really understand how Pachyderm can generate artifacts like reports or predictions, etc. My basic understanding is the data processing piece. Can you expand on how you can generate models, analytics, views, etc.? So yeah, and so if I wasn't clear on that, so basically Pachyderm is mainly concerned with / focusing on having version data and how that version data changes over time and applying code to that data. So if I have a, what's a good way to say this? If I have like a cleaning script for my data set, so say, well, actually, this is what I would commonly use it for. I have some very long audio files that I need to slice up into, say, 2-minute chunks, and then I need to align a transcript with those 2-minute chunks. So this is a little while back that I was doing this, so this is a more antiquated way of doing it. But so say I was trying to do that. I have my audio data that I'm trying to version and manage over time. I have my transcript data that maybe is being versioned and managed over time. And then I have a pipeline that's actually doing that splitting and then pulling in that transcript and applying that transcript to the different splits. So the reason, so Pachyderm itself isn't necessarily generating these artifacts and reports and those types of things, but what we have under the hood, this is kind of the mental model, is we have the files that we know that are coming in. So if we imagine, say I'm just mounting a drive to my computer that is my data, my version data set. I'm then running my code on that version data set and producing output files. What I can do is then take those output files and put them back into the version file system or in another data repository, for example. So this is basically, so the generation of artifacts and reports, it's your code that's generating those artifacts or creating those artifacts and reports. Pachyderm is mainly concerned with getting the data to and from. So you have data coming in that's versioned, you're running some processing on it, it's producing artifacts in the file system. So if you're writing files, and then at the end of that job completing, those files then get written back into the Pachyderm file system into a new data repository. So that's more or less how it works. I hope that kind of answers your question. But basically, you're using code to generate files. You're using code to write files, and Pachyderm is really kind of augmenting or, for instance, in Docker, mounting a file system that is allowing you to put things where you want them to be, and then those end up becoming data commits to output data repositories. There's a lot of really cool technical discussions there. I think I've put there's a bunch of YouTube videos that I've done on explaining kind of how that system works on YouTube, or even just look at our docs. There's some really cool stuff. So the last question I see here is, how do you connect determined AI to Pachyderm? So there's a few different, this gets back into kind of the flexibility of the system, which is really cool. There's a few different ways that you can connect the two. So one way is that you can, if you're doing experiments, so I have a huge data set that I've been working on, I'm versioning that data inside of Pachyderm. I want to do some machine learning experiments, some model training, and figure out just what's in my data. Can I train a model on this? Where are the gaps in my data set or in my model training? And so you're just doing some experiments. So in that case, you can just pretty much reference data sets that exist in Pachyderm. So Pachyderm itself has an S3 gateway, so it can kind of convert S3 type requests into Pachyderm requests and retrieve the data at a particular commit or on like the main branch or whatever else. So there are some ways to treat it from a model training kind of experimentation perspective. But another way is you can kind of flip the script. So say I have my model training process. I'm really comfortable with how this model training performs. It's doing hyperparameter search and everything else. My data is consistently changing, and I want to be training a model or at least kicking off training jobs so that I can know how, or so I can get like more relevant models over time or just automate this process. In that case, you can sort of flip the script by having Pachyderm, as the data is changing, kicking off training jobs using the API, the determined API, to kick off training jobs into determined and then getting those models back into the system. So say you have another pipeline that you want to then deploy that model to production or run some testing on that or something else. Automating that process from an MLOps perspective is where Pachyderm can kind of enter into there. So there's kind of different mentalities, and it depends on which kind of where you are in the kind of experimentation versus productionization journey as well. But using those tools in different ways can be really interesting. So the next one is, how far away do you think we are from solving the reproducibility crisis? So I would say solving it is a really interesting one. Like I would say it's kind of like, oh, how far away are we from solving kind of software development? It's more that with tooling, it's possible to reduce the number of issues, but data is never going to be perfect. We are consistently going to be curating our data, just kind of like our software is never perfect. We're consistently adding new features. We're consistently iterating on our software. We're consistently iterating on our data. And so there's always going to be new bugs and other types of things. Now, being able to get to the root of those bugs, which I think is, and provide, or like fix those bugs. Like, so there's data bugs, there's software bugs, but in order to fix those bugs, I think that's where reproducibility and transparency are most important. So I think as far as reproducibility, I think if we have data sets and model training code that are both verified and using deterministic algorithms, then I think it's pretty much solved. I don't think it solves the end problem of building models that are working in production necessarily. But I think in some cases, the crisis can be solved because we have reproducibility with deterministic algorithms. We have reproducibility with versioning our data sets. But applying it in a way that's consistent, reliable is usually the harder thing. Has been at least what I've seen. I may be more just avoiding your question than anything else, but I think it can be solved. I think it's really hard to do that on without tooling. I think it's relatively impossible or infeasible. But then with as you're doing it over time, I think you always come up with more situations that require you to dig deeper into your data or into your software that will seem crisisy, or you'll figure out there's one area where you didn't incorporate reproducibility. So for instance, you're logging inside of your production environment or something like that. The last question I see here is there any other platform that comes close to what AI at scale platform can do? So that's a good question. I mean, I definitely haven't seen all the different platforms out there. I come from the Pachyderm background, and so I'm pretty familiar with the data versioning tools out there and everything else. Everything that I've seen on the data versioning and data processing side, or data processing with data versioning in mind side, ends up being once you start trying to build that out with other types of components, you end up with Pachyderm at the end of the day. Just maybe you got there at a different, from a different perspective. But to my knowledge, I would say that there's probably, to be frank, like not really another platform out there that's taking the same approach that we are. I would also say that there are plenty of platforms that seem more seamless, or like everything kind of flows nicely together, but then it limits what you can do so significantly that you may not have that flexibility that you have. So it's a really tedious thing balancing the flexibility and scalability with simplicity, because the more simple you make things, usually the less flexible they are. And so I would say that it depends on kind of what metrics we're talking about. Does anything come close with the AI at scale platform? I would say for those types of things, like kind of balancing out the flexibility and scalability, I'd say probably not that I've seen. But if you're going more towards simplicity, there's a lot of things out there that maybe are more simple, but they aren't going to scale with you over time. And I think that's all for the Q&A. Yeah, Alex, do you have anything else for parting comments?
No, thanks so much, Jimmy. That was amazing. That's my first time seeing that talk full length, so I really, really appreciate it. I know other people did too. So folks, we're actually going to break for lunch. We wanted to thank Jimmy so much for joining and staying a little bit over definitely the time allotted. So we'll be sure to send out this presentation to everybody that attended, probably in like in a PDF form. So just to remind folks, we're going to take lunch for just over half an hour. We'll pick back up right here at 1 p.m. Pacific time or 4 p.m. Eastern, wherever you find yourself around the world. And just as a reminder, coming up at 1 p.m., we have end-to-end satellite data object detection demo from one of our solutions engineers. And then directly after that, we're going beyond GPT-4 and talking a little bit more about domain-specific AI training. So Jimmy, thanks so much again. Folks, we'll see everybody in just over half an hour.
Thanks. Take care.
All right. Welcome back, everybody. Just waiting for our next speaker to take the stage, Andrew Mendez. Obviously, we all have our day jobs, so and there he is now. Hi, Andrew. You hear me? Okay. Hey, Andrew. Can you hear me? See me?
Test, test. Is everyone able to hear me?
Yes. Hey, Andrew, can you hear us okay? I think you're on mute.
Oh, okay.
There you go.
How's that? Awesome.
All right, there we go. So welcome, Andrew. Thanks for joining us. I
Yeah.
was just explaining that obviously we all have day jobs, and so your day job superseded ML at scale, which is okay. So welcome. I'll let you do your introduction, and I'll
Yeah.
hand you the keys.
Okay. Yeah. Hey everyone. For those who are in the audience, I'm like excited to be here. So I'll give a brief intro about me. So I'm Andrew Mendez. So I'm in AI solution engineer at HPE. I've been with HPE for about a year now, and then previously I've been an ML engineer in the industry, where I've trained, tuned, and deployed AI models at scale. I've done object detection, object tracking, image classification, but I think kind of like all of my experiences and like all of my background, kind of it really can like boil down to I'm extremely passionate to help customers, being able to train, tune, and deploy AI models at scale. And so for this talk, I'll actually go through an end-to-end MLOps demo where we will explore some data. We will be able like to train an object detection model, and we'll also be able to deploy our model all within about 40 minutes. And this is using HPE MLOps platform. So like I believe now we do call it the HPE the HPE ML platform. And let me, rather than talk, I can show. So I'll share my screen. Okay. And so yeah, let me actually. Okay. So yeah, so what you're seeing now is a Jupyter notebook, and so pretty much what we'll be doing today, using the HPE MLOps platform, is we will build an end-to-end ML pipeline to train and deploy a deep learning like model, specifically an object detection model, to detect aircraft in overhead like imagery. So let me zoom in here. So before I go into to some live coding, right? A big question is that why, or how are we going to build this? Let me see if I can zoom in my screen. And so how we're going to do this is and then this can also help dive deeper into what is HPE's approach to MLOps or ML like in the wild. And pretty much, just from our experiences with a lot of our customers, and also being able to work really closely with leading industry experts, when it comes to doing ML ops in like the wild, there's three key things, right? You like need your data, you need good model, and you need good infrastructure. And how we approach our infrastructure is, we have infrastructure to be able to upload and also like to manage your data. Infrastructure to train like deep learning models at scale, and being able to like deploy your model to actually but to easily test and see how is my model performing in like the wild. And I think where the ML ops can really add value to ML engineers and also like the data scientists is these shouldn't all be separate. These should be all tied together with like the ultimate goal of, rather than having to manually, right, add more data, annotate more labels, and then having to manually kick off training and then to manually but deploy, this should be done all automatically. And the power with this kind of an automated like workflow is you can do really powerful things like being able to continuously train your model, on like new data, on like new labels. You can, but deploy and tune like a model really quickly to a specific like use case or mission. But if you wanted to really do some large scale hyper parameter search, this is possible as well. And so this is kind of an overview of what the HPE MLOps like, platform is. And just to quickly highlight, so this kind of infrastructure is built off of three key pieces of technology. So we have MLDM, which is the machine learning data management system, and this is based off of Pachyderm. So HPE acquired Pachyderm pretty recently, and they're like the leading platform to being able to both like to manage your data, also to be able to do advanced data versioning, but being able also to both like manage but to scale and to automate like any kind of pipelines, whether it's like data pre-processing, data management, or even end-to-end MLOps. So and then going into like our training infrastructure, we have MLDE, which is the machine learning development environment, and this is based off of determined AI. And then for being able to serve and but deploy your model, we're using a leading open source ML inference tool called Kserve. And to finally just take a step back, okay, so we have this infrastructure, we have these tools. How does this fit into the model that we're building? And so what we're going to see in this live demo is we're going to upload a small like version of our data set. So this is an object detection data set based off of a data set from the Defense Innovation Unit competition called XView. We're going to upload our data into Pachyderm. We're going to do some data exploration, and then we're going to train a model, and then we're going to we're going to deploy it, but after training, we're going to actually create an end-to-end ML pipeline that's using Pachyderm. And the powers are going to connect this pipeline directly to the data source. And then we'll see how we can easily add more data, be able to retrain a model, and be able to deploy it. So let's get started. And if there's any questions, feel free to interrupt me. And so actually, if people have questions, I won't be able to. Let me actually move this over here. Cool. So I can also see questions or any polls or anything. Actually, like a question, or this can be a poll that can be shared now or later. I'd be really curious to hear from the audience or even in the chat, what kind of AI models are you working on? Are you using PyTorch? Or are you using TensorFlow? As well as what are you using deep learning models? Are you using more traditional ML models? I would just love to hear, just because, I think the thing to really kind of highlight is with this ML infrastructure platform that we have, we offer like a lot of flexibility. So I see like the one person, so they are doing work like with TensorRT. So it's really awesome with Kserve is that should be able. So Kserve supports NVIDIA Triton, also TensorRT, and then for this demo, I'll be using under the hood of Kserve, specifically the serving tool called TorchServe. And so I guess the one thing before I start going through this end-to-end demo, just from like my experience training, tuning, but deploying models, I think to really highlight the need for good infrastructure, but also like the opportunities that it really provides to like the data scientists and ML engineers is, to really to deliver, great AI at scale and, at quick iterations. I think the key thing is to have good infrastructure. I mean, you do need good data, right? And you need like good models. But where most projects fail is in the infrastructure. I'll give a brief, thing or like a brief experience. I worked with like a leading DoD organization, like to help deploy object detection models for all these different use cases. And the biggest like bottleneck was, when we got new data, all of these challenges occurred in like different parts of this, really like this pipeline, right? If there's an issue like with data labeling, if there's an issue with our pre-processing code, and if there's new kind of classes and new things, right, we have to retrain our model pretty like quickly, but it was all done manually. And so, I think the power but to have a good infrastructure is like there is no need in this day and age to have to do this stuff all manually. Like there are great tools, but there are a lot of tools out there. And I think the main kind to take away from this talk is after kind of seeing, as a data scientist, as an ML engineer, but there are like great like tools, including our own, where you could not only train and deploy AI models with like great like confidence, but at scale. And so, okay, so let's start with uploading some data. Or I think to take a step back, I think the one thing to show is, okay, so we're going to be going through like the JupyterLab like notebook that includes all of our Python SDKs for both our training tool and also our data management tool. But let's take a look at it first. Just because as a data scientist, let's think, okay, I'm going to start the ML project. What does this look like? So first, we'll kind of see our data management. So we both have like a Python SDK, but we also have a great user like interface to be able to upload your data, also version, and also to explore your data set. So let me actually delete this repo real quick. And so what I'll show really quickly is we're going to upload a small version of our data set. And so we're going to also do a quick download and get a quick exploration of our data set. So as we see here, we have 225 images and there's 3 classes. And so we're going to detect 3 like classes. One is like a fixed wing aircraft, other like a cargo plane. And then also we have a small aircraft. And I think like the power, so we use like our Python SDK to upload our data over a Pachyderm. But now let's do like an inspection. And so what you see here, so like the power of Pachyderm is for every data, like the element that you do upload, there is there's an associated git like commit. And this is really powerful for being able to version your data and also to do a data provenance. So let's actually look. So we had 2 folders. We have our training data set and then our validation data set. Let me zoom in if we can do that. Okay, not. And let's take a look at a few of our kind of images. So I don't see an aircraft in this one, but we can kind of look and see. Okay, yes, we have a few kind of aircraft here. And also we've uploaded our data labels. Since this is object detection, we need like bounding boxes. So this annotation file has all of the labels that are corresponding to these images. And so now to go back to our notebook. So here we can begin to visualize, okay, so what do these objects kind of look like? And this is a key thing when you're going into deep learning, to really understand your data, because you can, easily check, are there any like labeling issues with their data? Is there any examples that are missing that are not labeled, or different kind of things like that. So I have some code that, so I guess to give some background, so this was implemented, so using PyTorch, and I have the PyTorch code that is associated with training this model. What I'm going to do is I'm going to move, just for the sake of time, because I think a key question that for data scientists and ML engineers, right, that are interested in like the HPE ML platform, how can like a data scientist or ML engineer, right, be able to take their deep learning code and integrate it into this ML ops like infrastructure? And so the first thing is to get your deep learning code being able like to wrap like for our training tool. And so like here's like a diagram that I think really describes how like a data scientist could integrate this into their workflow. So first, right? So determined AI, which is like the open source like version of MLDE. So we have two great APIs that are based in Python. That so you can take your you can take like your you could take like your best in class or like your favorite deep learning framework. So whether you have your deep learning code or like in PyTorch or like in Keras or like in TensorFlow, and all you have to do is take the core elements, and all you have to do is just like to wrap your deep learning code with our APIs. And I think I'll go into okay, you see trial API and also core API, but I think too like another thing. So we also need a config like .yaml file, and that includes all like the hyper parameters that that are key to like define your model, but you don't need in your code. And I'll go into why this is very valuable. And so for determined AI, you have two APIs. So you have like the trial API, and then you have the core API. So at a high level, if you have deep learning code that doesn't have a lot of complex like loss functions, but the deep learning code is easier to like to write and to like define, we have our trial API, which makes it really easy to integrate like deep learning code. And I'll actually show what the trial API is kind of right now. So all you need is a single single Python class. So we have so like the trial API, it's you just have to write your deep learning code in like the single like Python class. And so we have extensions for it if your deep learning code is written like in PyTorch, also like in Keras, and also like in TensorFlow. And so the core things for this class, you just need like your deep learning model. So here we're going to we just need like to wrap the model. We need like an optimizer. This is like an optional. If you want to do some cool things like with like your learning rate, we can wrap around that. So we have like the wrapping, and all you need to implement is 4 methods, right? What does like your data loader look like, or for like your training data loader? What does your validation data loader like look like? What does your train batch look like? And also what does your eval batch like look like? And I can already hear like the questions in like the audience. If you have very complex deep learning code that you already like written, how would this fit? And I think that's kind of where, so here we offer with the trial API ease of use into wrapping your deep learning like code, and then you can get all the great features and functionality with determined AI / MLDE. But if your code base is very kind of complex, we offer a really like flexible API like called like core API, which is all you would have to do, so you don't have to write a lot of new code to be able to fit your deep learning code into like a single class. We offer a lot of flexibility within like the core API, where you just have to be able to point where are like your checkpoints, where where are like your callbacks, and then you'll get all the features and all like the functionality of MLDE. And also, to answer the question, why would you want to hook your deep learning code into like Determined AI? Well, we offer some of the best in class like tooling when you want to train deep learning models at scale, right? When you want to go beyond a single GPU and to multi GPU, we offer like a distributed training out of the box. We offer also experiment tracking and also like resource management. And so we can kind of show that, but at least to take a step back, right? So all you need is like your deep learning code. You can either you can integrate your deep learning code using like the trial API, or you can use like the core API if you need kind of more like customization and to not, and if you have like a complex like deep learning code base. So feel free to ask me any questions in the chat. And I'll be able to provide my email address if there's anything that's not clear. And so I talked a lot about, okay, how do we wrap our deep learning code? Well, let's actually take a look at what does it look like to actually train a model just with like our training tool, because we did kind of get to see a little bit of what like Pachyderm like looks like, and I'll tie it all back in but together, so don't fret. So let's kick off an experiment, and let's actually so what's nice with with Determined AI is if you have a large team of ML engineers and also data scientists, and you have a lot of like deep learning projects going on, you can organize all your work like in like to workspaces. So I have my own kind of workspace, which is Andrew, and then here's my project where I train like deep learning models for this. So you can easily see and keep track of all of the models that I've trained. And let's actually look at the one that's currently training. So here's what an active experiment looks like. And so, what's nice is whenever you submit your deep learning code, we keep track of all like your code like artifacts. So here we're seeing all of like the runtime configuration settings. So here is a YAML file that we discussed where we kind of want to like define a key like hyperparameters. And then kind of also here's this single Python class that I've defined, and this using like the trial API, to kind of have our key like deep learning pieces that we need to like sort of train. And so, what's really nice is, like we automatically keep track of detailed logs. We actually have a built-in like profiler. So if you want to see, like is my code fully utilizing but the GPU that's available, you can easily keep track of that. And also here's our experiment tracking UI. So kind of what we have here, we can keep track of all of like our loss functions and all of like key object detection metrics. So we have MAP stands for mean average precision. I won't go into detail, but that's the key thing for object detection models, because we're predicting like a bounding box, and we have a ground truth that's like a bounding box. So MAP is really good at defining like the overlap of like of every model's prediction, and like the higher the MAP, the better. There's a lot of kind of metrics going on here. So here's kind of what I first look at. So I can keep track of, okay, so this is like the validation MAP. So this is my model's performance on like the validation, but you can easily kind of look at all of your training metrics and all of like your learning metrics. So what's nice too is, so just with this like single class, we have both like the distributed training out of the box, automated like checkpointing, and even like fault tolerance. So if there's anything that goes wrong with like with your cluster, we will keep track of to make sure that there is like a checkpoint, so that you can restart training. And I can hear a question from the audience is, okay, how would I go from one GPU to multiple GPUs, right? If you're a deep learning like a developer, you would need to right? Like write all this like distributed training code, and like here's like a huge like value like proposition that that Determined AI provides. All you would have to do, as long as your code is kind of wrapped either in our trial API or in a core API, all you have to do is change one setting, and this is like the slots per trial. And so here I define to only train one GPU, but you can change this to 2, 3, 4, even more that goes beyond a single node. And this deep learning experiment can like scale to like multiple GPUs and multiple nodes. So and I think what's really cool too, I won't get into the time, but so when you define all of like the hyper parameters in your YAML file, you could do a large scale hyper parameter search directly in the UI. And this is kind of what it looks like. So as data scientists, you have your baseline, and you want to do if you wanted to do like a grid search, you want to do like a random search, or if you want to do if you want to use our state of the art hyper parameter optimization search tool, which is based off of like the Hyperbit algorithm. It's all like accessible, all within the UI. I generally do my hyper parameter searches by using I create a new config file, but just to show that you can do this within the UI and you get this out of the box, which I think is really exciting. Anyways, so let's take a step back. So we train this model, and let's go back to our notebook. And so now what we're going to see too is the Determined AI like Python SDK. And so this is just a nice SDK that Determined AI provides. If you want to, within like a notebook, you don't have to leave. You can be able to download your checkpoint and actually be able to play with your model. And so I kind of already did that here. I think I ran into, oh yeah, let me rerun this. I added too many like classes, so that's probably why it failed to load. Oh, okay. Something else, like you can't always have like a perfect demo, so I'll keep going. But yeah, so but like with like the Python SDK, it's very straightforward to actually not only to be able like to download whether like the last checkpoint or like the best like checkpoint of your deep learning model, but also you can do some really cool things. So Determined AI has what we call a model registry, which that allows you to be able to pick a specific checkpoint and be able to save that into your into like your list of models. So if you want to explore it more, you want to deploy, you want to share your model, it's there. Let's actually take a quick look at it. So I have a checkpoint here where this is where I would upload it. I think, okay, here's one that has like a checkpoint. So I did this before to kind of see what it looks like. You can add notes but to it. Best model as of, here I'm just going to create like a note for my teammates, just so that other teammates can see, okay, like this is the best like checkpoint as of 2023. Let me actually, okay, let me just go from here. And so kind of just to see what like the model registry kind of looks like, and to take a step back, we have our trial API and our core API that's to help like with training models and to wrap your deep learning code. And we have a determined Python SDK to be able to do things such as explore your checkpoints, be able to load your model, and then be able, if you wanted to, use like the model registry. Okay, I said a lot of things. So now we can take a step back, and okay, so now we see what it looks like to what's like the tool to be able to upload our data set, to version our data set, and to train our model at scale. What does it look like to create an end-to-end ML pipeline? So let me actually have this to the side here. And so this is the power using Pachyderm, where you can create a pipeline that's directly connected to your data source. And this is really powerful because, right, as I said before, rather than having to kick off your training manually and having to deploy your model manually, right, being able to create be able to create AI pipelines that can define both your training and your deployment. then all you need to do is just, oh, and it's directly connected to your data source. All you need to do is just add more data, and it should be able to automatically kind of kick off training and to kick off the deployment. And so let's actually see kind of what that looks like. And so what we're going to do is using using a Python SDK that's provided by Pachyderm. We can all do this with Python code. We also provide both command line tools too. So like within the a command line, if you don't want to use like Python, you're able to create like pipelines as well. And so what I'm going to do now is I'm going to show what a kind of pipeline artifact looks like in Pachyderm, and kind of go into more detail. So I'm going to connect to the client again. And now this is our training pipeline. So I think the best way to describe this is, right, so we just saw previously that I kicked off an experiment in like Determined AI. So the power of Determined AI, right, you can submit an experiment. And if you wanted to do a single experiment on a single GPU, you want to do like this multi-GPU experiment, or you want to do a large-scale hyper parameter search. And so we're integrating that same code, but what we're doing is we're kind of having this this Python wrapper script that's going to kick off within this pipeline like artifact. And so the pipeline artifact, like in Pachyderm, we're defining it as like a JSON file. I think there's a lot going on here, but the main thing to note is with like Pachyderm, you have to connect to a data source. And so this is within like the input field. And so pretty much we define our data repos as repos. And so because I'm telling Pachyderm, you're going to kick off this training pipeline, and you're going to look for a repo named data, which we have here. And then all the stuff under the hood when it comes to being able to download your data, being able to provision, to provision this specific pipeline artifact. That's all done under the hood. You just, kind of need to, all you need is to define like your Docker container that you're going to drive like this pipeline kind of artifact. You just need like your input, and then you're ready to go. So we kind of seen what a pipeline artifact looks like. So now let's kind of kick it off. And so here we just saw in the UI, we created it like this pipeline artifact, and we can see this directed acyclic graph where we're pretty much like with Pachyderm or this pipeline, it understands, okay, I'm going to take data from the data source and I'm going to train a model on it. And so it's really powerful is just how in our data repo, we can do, really great like data set versioning, allowing like data provenance, but we can also version our pipeline artifacts, which is really powerful. And so kind of to see what our pipeline kind of looks like, right, we can begin to see some logs. What's powerful is because we're using the Determined AI code, we can easily just look at our experiment. So this is our cluster UI view, and I'm using a T4 GPU. So I can look at all of the jobs that are running now, and I can look at my experiment. And so now pretty much that same experiment that we ran is now being run within this ML pipeline. But now that it's connected within like Pachyderm, let me actually go back to here. Now, when we go back to our pipeline here, it's all kind of connected. I have a feeling this pipeline may fail only because I was doing some new kind of like customization. So, but the fact is that, kind of what we see here, kind of, right, like we're beginning to build this end-to-end MLOps like pipeline. I think if it does fail, there isn't like a need to fret. We can like keep on going. And so now something I can show what a deployment like pipeline also looks like. It's the same format, right? So we have a JSON file, and we have kind of like this Python driver script. You don't need specifically to use like Python. You could within this pipeline artifact that is running a Docker container, you could be able to kick off things with like a bash script or kind of whatnot. We're just kind of doing like Python just because I like Python, I want to keep pretty consistent. And so what this pipeline artifact does is we take the best checkpoint from determined or like from our training experiment. We're going to export the model. We are going to we're going to so we're going to take the best like checkpoint and we're going to like take like the model like dict which is like the model weights. We are going to then export it to a format for torch serve / kserve. And then we're going to deploy this onto our live kserve like cluster. So pretty much like similar format. We're also going to specify, okay, for some deep learning models, you just may want to use only CPU, but we also can, kind of use a GPU specifically to like deploy this model. And I think the key thing to highlight though is kind of how I showed that input where you have to define, okay, what is the input source? What we're doing is we're using training, which is a different name from what we have. So that, so it like did fail, but don't fret. But the thing to show the value here is this input source is like an abstraction to, okay, like where am I going to get the information that I need to then run this step? And so we're actually not pointing to a data source for the deployment pipeline. We're actually pointing to the training pipeline artifact. And so, as in like the similar kind of manner, we can, but deploy this pipeline and we can see it easily being able to run. And because the training pipeline didn't work, as it should, but the pipeline shouldn't run. And so this is really powerful because, if there's an issue with your code, you can immediately, have like this version artifact and, I don't have enough time, but you could go back to a previous artifact and, okay, like I know like this kind of pipeline artifact worked previously. That's what I'm going to do. Let me actually, since I have, and feel free to ask questions in the chat. I think I have a feeling the issue that happened was this. The training and deployment pipeline, they're grabbing stuff from the model registry. So it's checking, like, has this model like registered, like has this model been registered and is there like a checkpoint? So what I'm going to do is I'm going to delete both of like these model like registries. And I have a feeling I'm going to actually delete these artifacts real quick. So I'm doing debugging on the fly here, but just to show the power, just because I kind of work with this code a lot. So we're going to redeploy this pipeline and hopefully I believe this was like the issue. And, just to kind of, as like a data scientist, if you're doing like live, like deployment, actually, I already ran that pipeline. I'm going to resend the deployment pipeline. So, in the event that this training pipeline does work, let's not hold this MLOps pipeline back. Let's actually do like a deployment. And so, okay, so let's take a step back here. So we saw how we can integrate deep learning code to be able to train at scale. And we saw how we can be able to create an end-to-end MLOps like pipeline that directly connects to like a data source. So what could we do with this? And one really powerful workflow that you can do is you can begin to do continuous training. And so I won't like run this code just for the sake of time, but we can easily add more data with more labels. And because how we saw that pipelines all connected together, then we should be able to to re-kick off training and like deployment. Something that I was kind of working on too is, you can do more complex like workflows where, I could be able to show this in like I probably don't have time, but, if let's say you're a data scientist and you're like, my model with these two classes, or here we have three, we're getting okay results, but like we're missing some annotations, or we should define a new class to kind of have better class like separability. And that's really like also like a possibility too, because kind of once you write your key code, right, to train your model at scale and to like deploy your model at scale, these like pipelines should be agnostic to what it should be flexible, right, to handle new classes and new like amounts of data. And so, but there's so many other workflows that you can use kind of with this MLOps pipeline. You could do active learning, right? You could kind of do um, like the simultaneous, okay, let's like fine tune a model that's on the edge, but then let's continuously train good kind of AI of, let's say, foundation model, right? Kind of using a large scale hyper parameter search that takes a long time, needs a lot of GPUs. And so there's so many workflows, right? Kind of when you can take your deep learning code and automate it into like these pipelines. Let me actually see. Okay, so that actually did fix like the training kind of issue. So I'm really happy with that. And so, kind of now once that training pipeline did finish, now it's going to go through the process to deploy the model. So let's actually see what a live deployment looks like. So I don't need to run this. So these are different cells that that are sending unseen images to our API like endpoint. And once this is done, so as we're seeing, so so I already deployed our deep learning model trained on this new data previously. So now it's live. It's kind of ready. So right now, what we're seeing is our model is handling right like new prediction requests to data that it hasn't seen before. And what's really powerful with Kserve, I didn't go too much into Kserve, but it's like the leading, or it's among like the top open source ML inferencing tools that's available in the industry. So that if you have a deep learning model, if you have a non-deep learning model, whether like a PyTorch, Keras, NVIDIA Triton, by using like Kserve, so it runs on a Kubernetes cluster, and it pretty much can allow this horizontal scaling, but depending on what is that kind of workload, and so, okay, so what I did was I sent 33 batches of images, and now it's really powerful as we can begin to visually see our model's performance. And so I have these two sliders. So we have, okay, so the model is sending back all model predictions with a confidence threshold greater than 0.05. So there's a lot of noise, so we can actually begin to filter this. And because I already ran the predictions, we can kind of get that, we can get this feedback in real time. Okay, what's the best confidence threshold for this? And now let's look at, so 0.3 looks good. So now let's look at all of the kind of other images. Okay, so now we're seeing really interesting feedback. Our model, you can't always look at model metrics to get a feeling for your model's performance. Seeing it live, seeing it on unseen kind of images. And so now we can kind of see, okay, so this confidence threshold is a little too high. Let's see. And we're getting a lot of false positives. So I think this model just needs more data and more training. But here's the key thing, right? To do this without an MLOps platform, how long do you think this would take to sort of get this value add back to kind of see how your model is performing and be able to quickly kind of iterate? From previous teams that I've worked on, this would take weeks or even days, and so here we get this immediate feedback that then we can kind of really go off to the races on. And so yeah, so here's an interesting example too, where there's clearly a plane there. We should be able to see that. But let's see, if I lower the confidence threshold, okay, it does pick it up, but it has it's not the best precision recall. But we can kind of see, okay, if we trained it longer, we trained it on more kind of images, this model should get better. And being able to do this in an automated manner really reduces the time to value faster. And yeah, I think with that, that's the end of my demo. Would love to hear any questions from the chat. Yeah, if anything, because I went fast to kind of really go in depth. But I'll lecture my email on the chat if anyone has any specific questions. But feel free now to sort of ask any questions, and yeah, I would be extremely happy to answer. See Slack. Okay, let me actually go to the Slack. Some people are asking questions.
Andrew, thank you so much.
Yeah, do we have any questions in the chat? I want to make sure I'm not
I
missing
think
any.
it was just the one from the Q&A. I wanted to make sure, I'm assuming the answer is yes. If folks do want to try this end-to-end example out, is that something you can make available to folks after the session?
Yeah, so I'm trying to think the best way to, I can point to our open source code base that we have that has not this up-to-date demo, but you can look at the code and kind of begin to see, okay, like what would it look like to, integrate my deep learning code, and kind of see like a pipeline kind of looks like. So I can share that, but like be warned, it's under active development. I think something I would recommend, because how I learned to be able to build this end-to-end like platform, right? First I would kind of have a good deep learning example. So I would look at but the determined AI examples to be able to easily see what it looks like to to train a model using the determined AI platform, and also look at the Pachyderm examples too. I think that code is going to be approachable to kind of see, okay, how would I create a pipeline, and then how would I train a model on the determined, and then let me look at actually. So what I'll do is rather than showing the teams, I'll just actually, I do have the actual, okay, here we go. So this actually has, so I'll share this in the Q&A, or should I share this in the Q&A? I can share the reply. A reply, okay, here we go. Yeah, so I'll share it. So this is my like personal kind of GitHub, but it's under a lot of development, but you can kind of take a look at it. But feel free to reach out to me. I feel like I really love to talk to other like data scientists and ML engineers. And I think there's a lot like to that goes into, right? Like, does it make sense to create like an ML ops like pipeline, or do you just need, just a good like training at scale like software? So I think that's, yeah.
Yeah, and is the easiest way to do that over email or Slack, Andrew? What do you prefer?
Yeah, either or. So I'm on the open source like Slack community. I'm also you can reach out to me at sorry, andrew.mendez@hpe.com. Again, andrew.mendez@hpe .com. And yeah, I'm extremely excited to hear anyone's like questions and any way that I can help.
Awesome. Truly showing ML at scale all the way through. Thanks so much, Andrew. That was an amazing presentation. Really appreciate it. For those asking, we'll obviously make these recordings available on the Hopin platform, as well as our YouTube channel, and maybe over email as well, like Andrew mentioned. So we've got about 10 minutes before our next session. So for those of you that want to stick around and ask Andrew any questions, he'll be on this session. For those of you that want to catch our final session for ML at Scale, wow, that's amazing. Coming up in 10 minutes, we've got Liam over in a separate session, the one that's titled Go Beyond Go Beyond GPT-4. So Andrew, stick around. Everybody else, we'll see you over in the other session. All right, welcome everybody to our final session for ML at Scale. Want to welcome Liam Lee to the stage. Hi, Liam. Good to see you again.
Hello, just trying to get everything set up over here.
You got it. We'll let a few people trickle in from the last session. All right. How's it going, Liam?
Can you hear me?
Yes, we can hear you just fine.
I don't know why I can't hear you now.
That's all right. Any better? Give Liam just a few minutes to get started, audio and video wise. Oh, you're muted, Liam. All right, any better, Liam?
Yes, I'm
All
back.
right. There we go. Save the the technical difficulties for the end. So thanks for joining us, Liam. Wanted to welcome you to the stage. Thanks again for showing up. This is our final session for ML at Scale, which is hard to believe. We'll make sure to post the recordings from all of our sessions today, both on Hopin, on YouTube, and perhaps in the Slack as well. If you have any questions, feel free to put them in the chat, post in the Q&A, or otherwise feel free to request to come off mute towards the end of the session if you do have questions for Liam. And without further ado, I'll hand it over to you, Liam.
Yeah, it's great to be here. And today I'll be talking about how to harness the power of LLMs in industry. And we're going to try to see a few ways that you can go beyond just calling OpenAI APIs or other third-party APIs and really own the experience and the model yourself. So, just to set the grounding and make sure we're all on the same page, I want to give a brief intro to LLMs and think everyone has probably interacted with them or used them or even fine-tuned some of them yourself. So I'll keep this part short, but we've seen that these massive LLMs emerge that seemingly can understand, explain, and generate new content. And with these large language models, they're all basically massive transformer type models that have been trained on hundreds of billions of tokens and have seen so much data and are so large and capable that they have been able to achieve almost human-like performance on various downstream tasks. And the amount of innovation in this space has been very drastic, very quick, and even very recently, we've seen two very powerful open source models released, including Llama 2 from Meta Facebook and also Falcon from TII that are approaching the performance or match the performance of some of the most powerful closed source models. So we'll talk a little bit more about that in a bit. But we've seen a lot of development in this space, and I think it's really exciting. So taking a look behind the scenes, I mentioned that these are all transformer style models, and they're basically also all trained with a single objective. And the objective is really simple. The language model is basically trained to learn the probability of next words or next tokens given a sequence of text, right? So that's the training objective, is basically like minimize the loss associated with predicting the wrong next word, right? So the language models, how they are trained and also how they're used in practice is, let's say we give the language model an input like, this 23-year-old female has complaints of allergies, and in the past she has tried Claritin. And we give this to the language model. The language model will hopefully have learned the relevant probability distributions to complete the rest of the sentence, right? So we hope that the probabilities will place much higher mass or more weight to other types of antihistamines like Benadryl, Zyrtec, etc. Right? So I think it's very useful to always keep this in mind. Like behind the scenes, all these language models are basically probabilistic models of different sequences of learned over many sequences of words. So what's amazing is that from this very simple modeling problem, we see very surprising abilities emerge. And this is evidenced by the performance of the, for example, in this case, GPT-4 on different tasks. And a lot of these tasks shown in this chart here are sort of exams that we use or tests that we use to evaluate human intelligence, right? So, we see some AP tests here. The LSAT is also included in this set of tasks, as well as some medical exams. And first of all, like GPT-4 is a big improvement on GPT 3.5, the previous version of ChatGPT. And in a lot of these tasks or tests, GPT-4 has been able to match, leading or match human performance, or in some cases even exceed human performance, average human performance on some of these tasks. So I think it's really exciting, the types of applications that are possible for these language models. And for us and for you, if you're working in a company or you're just in some role where you want to basically investigate or start applying LLMs to your problems, there are quite a few opportunities to do so, and the levels of customization that are possible with LLMs kind of are shown in this pyramid, and the pyramid is kind of organized in increasing amount of compute that's required. But there are many different forms of customization and ways of applying LLMs to your domain specific problem. And the easiest entry point is definitely prompting. I think probably lots of people have tried some of that already. So it's great if you have. If you haven't, we'll do a quick overview. I think after prompting, the next level is fine tuning, where you're taking like a pre-trained model and injecting your own domain specific data into it and updating the model weight so that it'll hopefully perform better on a domain specific task. And then finally at the top is that level of customization is pre-training, where you're basically training a model completely from scratch on custom data sets. And obviously that takes a lot of compute, so we won't spend too much time talking about that, but I'll touch upon it a little bit. For this talk though, I think the focus is definitely on how you can go beyond just calling the OpenAI APIs yourself and why you want to do so. So we're gonna, and I think the main benefit of really starting to own your models come through in fine tuning. So kind of build up to understanding what, like the reasons you should start to fine tune your own model instead of consuming an API to fine tune, etc. So I'll talk about all of that kind of under the lens of owning your own model, taking an open source model and applying it to your problems. So, we'll see definitely the benefits of fine-tuning your own model and starting with open source models. But I think the main consideration for going the route of APIs or using an open source model is like how important it is for you to maintain control over the model and how it's being used in all of your applications. Excuse me. So, this is definitely a core consideration, and this is a consideration in addition to definitely all the benefits that come from being able to fine tune and have full access to model weights, etc. Right. So, I think one key consideration that we hear a lot is it's very important for some organizations to keep their data private and secure. Another consideration is around kind of model alignment. So if you use something like ChatGPT directly, it has been aligned for specific characteristics, right? So if you have different alignment criteria, I think that's another very good reason to control your own model and be able to control the alignment trade-offs. So, and what I mean by that is, so here in this chart, I'm showing 6 different dimensions corresponding to alignment and comparison of an instruction tuned model. So this is ChatGPT, an older version, compared with the base GPT-3 model, which hasn't been kind of fine-tuned for alignment, right? So if you use ChatGPT, you can see that it has very different characteristic trade-offs from the base model. And in particular, I think the one dimension that some use cases could really care about is calibration error, which basically means, how much can you trust the probabilities of predicted probabilities of your language model, which can be used to like score uncertainty of a prediction, etc. So, if you're in a use case where those probabilities are very important and you need to know how confident a generated text is, then calibration is also very important. And this is one dimension where we see the calibration error is much higher for the instruction tuned version than for the base model, right? So there are a lot of these alignment type considerations where if you feel strongly about particular alignment behavior, it's also a very good reason to own your own model. Other benefits and aspects of having control is you will also have control when and how a model changes. So there have been many examples of OpenAI updating their model and then suddenly a prompt or an application with encoded ways of interacting with the model stopped working because the model and the associated instruction tuning and alignment has changed, right? So it's also important in some use cases to be in control of when the model changes so that your system doesn't break and is not brittle to upstream API changes or upstream model changes from OpenAI. And finally, if we go the route of open source, we have access to the weights, to the training code, evaluation, etc. Gives us a lot of flexibility in choosing, different algorithms that we use to tune or to fine tune and train further for our use cases. So I think this is definitely the first starting point. Is how important is control, and then the benefits of improved performance and reduced cost. I think will come when I'll talk about them more when we dive into how to use LLMs for your specific use cases. So as an outline, I'll give a quick overview of applications of prompting, and then we'll talk about fine tuning and kind of glue those together into an application deep dive on an information retrieval / retrieval augmented generation use case, and then end with a small reference to some pre-training that could be of interest to some folks here. Okay, so prompting is definitely the easiest way to get started with LLMs, and I think people usually associate prompting and in-context learning together. And if you're not familiar with in-context learning, we'll kind of differentiate between standard usage and in-context learning now. So, the very straightforward way of interacting with the language model is just to basically use it to help you answer specific questions or extract knowledge from the weights from the trained weights, right? So this is an example of something that's not what we'd consider in-context learning. So we're just asking the model to answer a question, and it has to answer with the information that's already been encoded into the weights, right? So this is a negative example of in-context learning. There isn't really in-context learning here. It's just standard generation from a language model. The in-context learning version of this example would be something where, we don't just rely on the model weights and the information stored in the model to answer the question. Instead, we might provide some references of text that contain information relevant to the question, and then ask the language model to answer using those references, right? So then the model becomes more of a reasoning system that's connected to the knowledge, both the knowledge that's already in the weights, but also the knowledge that's provided in the context, right? So when we see in context learning, it's really like this ability to reason, and it's a primary way of applying prompting to new applications that a model might not been directly trained to perform, right? So just to make things a little bit more concrete, let's think about a case study where, let's say we are a radiologist and we have like notes from radiology studies where we have like a passage of the notes and then a question, and we want to be able to determine whether the information that's contained in the passage can be used to answer the question or not. And that's kind of what the label of entailment is. So if the passage has information needed to answer the question, then we would label an example entailment. And hopefully it's obvious that this is a form of in-context learning, because the passage contains information relevant to answering or to performing the task, and we're just asking the model to use the passage and reason about it in order to be able to give us a label of entailment or no entailment. So there are quite a few different types of prompting and some templates, right? So the simplest form of prompting is what we call zero-shot vanilla, and the zero shot here corresponds to basically not providing any additional examples. And this is basically what we saw before, where we give a system prompt that provides the instruction for the task, and then we give the sample that we want the model to provide an entailment or no entailment label for. So this is probably the most straightforward form of prompting. Can make it a little bit more advanced by turning it into a few shot version of a prompt, right? So now we can add additional examples of labeled samples from our data set. So that's what's kind of going in the middle. And hopefully the language model can look at those examples and figure out what it's being asked to do for the input query that comes at the end. There is another very popular form of prompting called chain of thought reasoning, where a language model is asked to provide an explanation. And this is similar to what, as a human, you're asked to do when you complete your math homework, to show your work instead of just providing the answer. And hopefully having to think through it will allow the language model to provide a more accurate answer here. And then there's also certainly a few shot version of this where example explanations are provided. So how does few shot, or how does prompting work for this sort of radiology task? So here we're looking at the performance of both ChatGPT and GPT-4 with zero-shot vanilla and zero-shot chain of thought reasoning on this radiology entailment task, right? So we see kind of the logical correlation here, the pattern where obviously GPT-4 outperforms ChatGPT, and asking a model to explain its work with chain of thought reasoning gives better performance than just having the model generate an answer directly. So this all makes a lot of sense. Now, if we also include results for the few shot version, we see behavior that's a little bit unexpected, right? So the expected thing is that few shot should do better than zero shot, because we're including examples, and hopefully the model is able to learn from examples and outperform the zero shot setting. So we definitely see that pattern for both vanilla few shot and chain of thought few shot. The thing that is counterintuitive is that the few shot chain of thought version of prompting actually does worse than the few shot vanilla. So for some reason now, if we include explanations for the examples, the model is actually not able to learn as well from those examples and actually performs worse than the vanilla few shot version. So I think this is really interesting. It really indicates there's some gap in knowledge in the pre-trained model. And this really gets at one of the limitations of prompting where, we want to stuff as much information into a prompt as possible, but there are obvious limitations around like the maximum sequence length that can be passed, but also around how well a model can learn from long contexts. So in other work, they basically studied how well GPT 3.5 or ChatGPT is able to extract an answer from a long context, and the performance of ChatGPT depended on where the answer was in the sequence, right? So if the answer or the passage containing the answer is closer to the front or it's closer to the back, then the performance was much better than if the answer was in the middle somewhere. So even with long sequences, these models are not always able to retrieve or identify the right information from a long context. Another reason that sometimes prompting is very limited is language models really struggle to learn long tails of knowledge. And this in prior work, we basically saw that by Kondo Paul et al., we saw that for things that showed up a lot in the training data set, the language models were able to learn and perform very accurately on a downstream task. But for things that are not very do not have a lot of representation in the pre-training data set, the performance was much worse, right? So you can use this to reason about why chain of thought didn't perform as well in the few shot version, and it's because probably the amount of radiology knowledge that's encoded in the pre-trained model is probably not as high as you'd really need it to be in order to learn from the explanations. And this is where I think fine tuning can help a lot. So, fine tuning provides us a way to really inject a lot more information into these large language models by updating the weights themselves instead of just relying on in-context learning. And they're not really mutually exclusive. Like you can fine tune and still use prompting. And so, to continue the example before, we can train, I can fine tune a base language model with the examples that we have for radiology and, and have it learn from that to generate the labels directly from the data that we have. And because we're able to provide a lot more data to fine tuning and have it basically learn from thousands of examples instead of just the 10 examples that we can fit into a context window, we kind of see this sort of performance curve where, as expected, the more data that you have to fine tune on, the better the fine tuning performance. So in this case, with the full training data set of close to 8,000 data points, some of the fine-tuned models are actually able to outperform 10-shot GPT-4. And these fine-tuned models started with a base model that was much smaller. So if we then use the fine-tuned model and for the tasks that we care about, that also means that inference is much cheaper and faster. So there are definitely situations in which fine-tuning make a lot of sense. And there are a few desiderata, right, for when you should use fine-tuning versus prompting. I think the first takeaway from the case study that we looked at just now is prompting, especially with some of the latest state-of-the-art LLMs from OpenAI, it establishes a very strong baseline. So we do need to be careful to like when we're trying to decide whether to fine tune or not, because sometimes maybe prompting is just the right way to go. But there are definitely benefits to be had from fine tuning, as we saw in the previous chart. So that really depends on a combination of the uniqueness of the domain that we're talking about, how complex a task is, and also the availability of data. And I think another thing that definitely influences decisions for fine tuning is if your application or your model or your application needs to serve a lot of users, the inference costs can get very high if you're just calling OpenAI API directly. And in the radiology case, with the lengths of examples that we have, it was around 3 cents per request to GPT-4. So if we're talking about hundreds of thousands of requests a day, that the cost can scale up very drastically, right? So in those cases, it could make sense to explore fine tuning so that you can get a smaller model that achieves similar performance, but is much faster at inference time or much cheaper at inference time. So what are some of the tools that are available to us today to fine tune large language models? And I think more and more, like, the viability of pursuing the fine tuning route and owning your own model is much more reachable with the introduction of really capable open source LLMs like Falcon 180 billion as well as Llama 2. So, like, it's definitely very viable to go the route of fine tuning and owning your own models today. And there are a few ways that we can go about fine tuning. Traditionally, in the computer vision domain, in the early days of LLMs, we usually perform what's called frozen pre-trained fine tuning, or frozen fine tuning, where the feature extractor modules are frozen or fixed, and you're only really updating the prediction heads that sit at the top. We've moved away from this because there have been lots of observations and data points for full fine tuning where the entire model is being updated performs much better than just updating the prediction layers for LLM type tasks. So, this sort of full fine tuning can definitely get very challenging when we're talking about models that have billions of parameters. And I think this is, like, to understand the scale of fine tuning and training. We can look at this table, which basically shows some of the GPU memory requirements associated with different models. So if you think about like a 20 billion parameter model, the GPU memory that you'd require to perform fine tuning is, if I sum it all up, is basically it's 320 gigabytes just for weights, gradient, and the optimizer states. So the amount of GPU memory required for training, it explodes pretty drastically. So that definitely introduces a lot of challenges when we want to fine tune these models and perform and update all the parameters, because if we're even talking about the 20 billion model, the models obviously do not fit on even the largest GPUs, and we start needing to resort to forms of model parallelism or resort to specialized libraries that, like DeepSpeed, that can shard certain parts of shard the optimizer state, for example, or support activation checkpointing to further reduce the GPU memory usage. So, these libraries, it's really helpful that these libraries exist, but they definitely come with learning curves, and they need to be optimized in order to give the highest throughput and efficiency. So, this is where I think, there are various tools that are available to help with that. I think Hugging Face has made it very easy to use some of these advanced techniques, and you can also use them with Determined, and we can help you tune the performance of these more like model parallel or large scale distributed training libraries as well. So even though it's challenging, I think more than ever, we have tools now to make it more easy, much more like tractable. So, I think there's also been a lot of interesting development in the realm of parameter efficient fine tuning. So, these approaches basically all take some flavor of updating just a portion of the weights instead of all of the weights of the model. And probably the most popular one here is LoRA, which stands for low rank adaptation. And you can see some of the approaches even get down to just like less than 0.1% of the total parameters. This reduces the need for like GPU memory associated with the optimizer state, but it's still, you still need to be able to kind of fit the entire model into memory. So, it's more tractable with these approaches. I don't want people to think that, PFT is a full replacement for fine tuning, because there are definitely situations in which full fine tuning still does much better, which you can see in the second table here on the bottom, where full fine tuning gets to like 0.71, whereas something like LoRa only gets us to 0.6. Right? So there can still be a big gap sometimes, but in a lot of situations, PFT also makes it easier to fine tune these large models. So, it wouldn't be a determined conference without some mention of how we can help you solve these problems. And you can use all the techniques and all the models that I talked about with the Determin ML/ML machine learning development environment platform. And we have kind of the capabilities of experiment tracking, resource management, hyperparameter search, distributed training, all there for you so that you can take advantage of these large language models and fine tune them very easily. So here I'm showing an example of fine tuning a Llama 2, or fine tuning an instruction tuned Llama 2 model called the Vicuna 7 billion with LoRa. So it's very easy to use the same sort of these techniques within MLDE. Okay, so we talked about two ways of using LLMs, prompting and fine tuning, and in particular, how you can do this without using third-party APIs and instead own the models yourself. So I'm going to pull this all together into an information retrieval application. And there's a lot of interest that we've seen from customers who want to deploy this type of application for their problems or develop these types of application for their problems. And a lot of the motivation comes from the desire to reduce LLM hallucination. So, even in a very simple example like this with GPT-4, if you ask GPT-4 directly where the McDonald's is at the Seattle airport, it's going to answer incorrectly and say that the McDonald's is near gate C2, when in actuality, the McDonald's is close to the B gates. So this is kind of what people are referring to when we talk about LLM hallucination. And the reason that this happens, it really goes back to one of the first few slides. It goes back to, it's associated with the probabilistic nature of language models, right? So the language model has somehow learned that the completion for where, like, the answer to the prompt of like where McDonald's is, it's more like, it's seen more situations where it's determined it's more likely that the answer is C2 than B gates. So, one way for us to bypass this sort of hallucination is with like retrieval and in context learning. Right? So if we can pull in a fact and inject the fact into the prompt and then have the language model answer, then there's a higher likelihood that we can be correct, right? So like in this case, the retrieval augmented version, retrieval augmented approach to this would be, maybe I go to Google and make a query and ask where the McDonald's is at SeaTac Airport, get the answers back, inject it into this prompt, and then have the language model synthesize an answer. And that's basically exactly what we did for a POC, where our customer was interested in developing a question answer system for finance specific articles, right? So here, we could have tried to build such a chatbot by just like asking a language model directly and injecting all the information in these articles into the model via standard fine tuning. Another approach, and this is the approach that we took, which is more of a retrieval augmented approach, is to have a separate retrieval system that will select relevant passages for a question and then have a LLM then synthesize an answer using the retrieved information. So, this basically looks something like this. If we get in a question like, what is the idea behind using gaming simulation techniques in scenario planning to tackle economic crime more effectively, we'd be able to present the sort of UI on the right, where we'd also be able to show the relevant documents that were used to answer the question. So there are two core components to information retrieval application. One component is a vector search system that's in charge of returning the relevant passages. And then another component is kind of the chat module that's needed to understand user intent and synthesize the answer given retrieved passages. So how does the vector search component work? It's pretty straightforward. And vector search is definitely not something new. It's been around for a long time and has been used a lot in recommendation systems, semantic search systems. It's just that now they can be a lot more powerful with the much better text embeddings that we have with larger language models. So the way that a vector search and vector store works is that we need an embedding model that gives a vector representation of our documents. And also it can give us a vector representation of a question when a question comes in. So the first step is to basically take our knowledge database, generate text embeddings for all the documents that form our knowledge store and put them into the vector database. And then when a new question comes in, we can use the embedding model to create a vector that represents the question. And then the vector store is in charge of returning the most relevant documents, the most similar documents for the question or query vector. So this is pretty standard, and you probably heard of quite a few vector search stores or vector stores like Pinecone, Novus, Weavy, etc. They all do something similar underneath the hood. And then the chat model, like we said before, is used to synthesize the user question, the passage, and return the answer. So you can imagine like prompting would definitely be, is definitely a relevant portion of this, where we might want to add a prompt to the user question and the passages so the chat model is able to give us a better answer. Fine tuning is also can improve the performance of retrieval augmented applications, and in particular, a lot of improvement can be had from fine tuning the embedding model instead of the chat model. And the intuition for why you'd want to fine tune an embedding model is basically, if you have a standard embedding and let's say you're consuming just OpenAI's embedding model, it's not really specialized to a particular domain. So when we look at the projection or embedding of all like articles of different subjects, you might see some sort of clustering like this that's good at differentiating the high level topics. But if we zoom in on business and finance, it might look very like the boundaries might be not very well delineated at all for sub types of within finance, right? And intuitively after fine tuning, we should have a model that's much better at differentiating like nuanced sub areas of finance and banking. And that's exactly what we observed for this POC, where we basically compared the retrieval performance or retrieval accuracy of OpenAI's ADA embeddings with a base open source embedding model called SGPT, and then our fine-tuned version of that embedding model, which is the third row in the table here. And we compared the performance of both just dense vector similarity, so that's the first column under vector, and also a combination of standard keyword search as well as semantic dense vector similarity, which is under hybrid. And basically, we see that the fine-tuned model is actually able to outperform ADA embeddings, although the base SGPT model that we started from for fine-tuning underperforms ADA. So we do get signal that this sort of fine-tuning of the embeddings can help a lot when your domain is differentiated enough from standard or a general typical text. So, the HPE software suite of MLDM, which is the enterprise version of Pachyderm, and MLDE, the enterprise version of Determined. And this also holds for the open source libraries. But the tools together make it really easy to develop and deploy pipelines for an information retrieval application, like the example that we just saw. And this basically shows an example pipeline of what a deployment for a RAG application would look like. So in our case, we have a combination of the articles that we used or we wanted that formed the knowledge base at the top, in addition to labeled question answer pairs that we generated using a strong language model. And these kind of go and form the training data set as well as the vector database that gets created after our embedding model is fine-tuned. And both the model and the vector database, embedding model and vector database, and are then connected to a Streamlit app that is serving the interface to this sort of application. And the nice thing about doing this within MLDM or Pachyderm pipelines is it's tied to a version data set. So if we have new articles that we want to include in the knowledge base, it would basically create a new version in the cache management articles node within this pipeline and flow the new articles through to the generate vector database so that our knowledge store is updated automatically, right? So we can do incremental updates with a deployed pipeline like this, and also just track everything that's happening in a deployed application. So, talked a lot about this. I think just to summarize a little bit, LLM-powered information retrieval has some really nice benefits and pros. In particular, we talked about first about how it reduces hallucination, also provides auditability because we can see exactly what information passages the language model referenced when it was creating an answer. It also gives us a way to separate the knowledge base from the language model so that our knowledge base can evolve much faster than the language model, and the language model doesn't need to always contain the answer. The answer can just exist in the vector search knowledge database. And finally, because we don't need to like for example, in the case of long documents, we wouldn't be able to put all of it into the same context, but we can chunk it up and put it into our vector store. And this gives us a way to retrieve just the relevant pieces of long documents and bypass the context length limitations of standard consumption of a language model. So, I think all this can kind of be synthesized into a decision table that looks roughly something like this. And I think Intuit really covered all the desiderata that we talked about in the slides, but it's kind of all gathered into one place for reference. So you can come and look at this later, but this is kind of the framework that I use to think about the appropriate approaches for different use cases of LLMs. So, finally, I wanted to talk a little bit about pre-training and how pre-training is applicable to specific industry use cases or custom domain use cases. And we've seen domain-specific models pre-trained for finance and medical use cases in the form of Bloomberg GPT, as well as like Gatortron, which is a medical like patient transcription model, that medical electronic records model that was trained. I think with the release of the latest language models, those domain-specific models haven't been as strong. But one domain in which domain-specific models are still really powerful is in the domain of code, and I think this domain gives a lot of indication for the power of pre-training in other industry domains. So we've seen kind of code specialized models in the form of StarCoder, LlamaCode, and WizardCoder. And a lot of the times when people talk about pre-training, it's it's under the assumption that we're talking about pre-training completely from scratch. But there's also what's called continued pre-training, where you can take a pre-trained language model like Llama 2 and continue to train it on, in this case, code-specific text, which is what's done for LlamaCode in the second row here. So StarCoder is completely pre-trained from scratch on code text from GitHub and GitHub issues, etc. LlamaCode is basically continued pre-training on top of a general language model, Llama 2. We've also seen Llama Code Python, which is continued pre-training of Llama Code with Python-specific code. And then finally, there are also instruction-tuned versions of code models that build upon kind of arbitrary base code models, which is Wizard Coder, which has variants that are built on top of Llama Code, as well as Star Coder. And there's the relative performance of these models is actually really interesting, and I think also quite compelling for like arguing for training, pre-training or continued pre-training domain-specific models. So here we see that the performance of the instruction-tuned Wizard Coder fine-tuned on top of Llama Code Python is the second best coding specific model for the human eval data set, right? So, or for the human eval set of tasks. And it's second only to GPT-4 and actually outperforms ChatGPT as well as Claude 2. We also see, like, I think another surprising result from this is that the code specific pre-trained model Star Coder, which is the second one on the right, outperforms a general language model, Llama 270 billion, actually. So there's definitely benefit to this continued pre-training or domain-specific pre-training. And I think another really interesting takeaway is that the instruction-tuned version, so basically anything that's Wizard Coder, outperforms just like in-domain pre-training. So the instruction tuning actually is very important in getting the best performance from your domain-specific models, and probably indicates that when we extend these results, or if we try to reason about pre-training and the effects of pre-training for a new domain, there's probably there's an instruction tuning, there's probably further instruction tuning that we can do for new domains with instructions specific to that domain that would help with downstream performance tremendously. So that kind of concludes my talk. I want to summarize and just talk about a few reasons why we should consider going beyond consuming third-party APIs directly, like from OpenAI or Anthropic, Cohere, etc. Just again, I think the first desiderata and a really important one is just how important is it for you to maintain control over your data and the model. And then the other two are, if we go the route of owning our own model and really taking advantage of fine-tuning or continued pre-training, it often translates into improved performance because we can learn from all the data that we have collected specific and relevant for our specific use cases. Also means kind of translates into reduced costs with fine-tuning, because oftentimes we can train a much smaller model to perform just as well as a large language model. So, I think all these are reasons that we'd want to go beyond GPT-4. And if you find yourself in some sort of in this sort of situation with some sort of desiderata like this, I think it can be really helpful to explore the promises of fine-tuning and owning your own model. So I want to maybe just look forward a little bit, and I think we've seen a good amount of development in this area as well. But everything I've talked about is certainly relevant. But they can all be components in a larger knowledge augmented LLM application. So we've seen different industry. We've seen situations in which just using prompting or fine tuning to apply LLMs to a task is insufficient. So InSilico but there are actually other ways of using LLMs by connecting them to domain-specific tools like knowledge graphs or other tools in the case of chemistry, where you can really like inject information or have a language model interact with these tools as in the form of an LLM agent. And that oftentimes bypasses the limitations of the language models themselves. So we have an example from InSilico. We also have an example from this ChemCrow paper where they found that if they ask the language model directly to come up with a synthesis plan for a new chemical, it would often fail pretty drastically. But if we connect the language model to domain-specific tools that are able to that the language model is able to use and chain together, then it can come up with a plan for synthesis that's much more accurate, right? So I think this is really where I'd expect to see a lot of development in the future of connecting everything we talked about, like building domain-specific LLMs to domain-specific tools to really derive the most value from these general language models. And that's all. So I'm going to stop here, and I think we have time to take some questions.
Liam, thanks so much. There's a few questions in the Q&A section, if you can see that on the right-hand side. And while you're flicking over to that, I just wanted to remind folks, if you do want to come off mute and ask Liam any questions yourselves, please feel free to do so.
So we have a question about code LLMs and whether we think organizations will invest in building their own LLMs that sit on top of their code bases as opposed to using ChatGPT. I think, I would say yes if I were, if I was kind of in the position to decide whether I want a code LLM that I develop my own or I use ChatGPT. I think a lot of organizations will choose to own their own code model because they don't want to share their proprietary code information. I think we can also, like the instruction tuning portion is quite important. You can actually do instruction tuning pretty cheaply and have, let's say have some of your developers write their own instructions specific to your code base that would actually help it perform much better than a general code model. Cool. I don't know if there are other questions, but happy to take any offline if people have them. And thanks for everyone's attention. So I think I don't know if, so in the example I showed, so there's a question about, do I see knowledge graphs as a key enabler of LLMs in industry? I think absolutely. So the example I showed, I wouldn't really consider it a knowledge graph. It is a knowledge store in a kind of flat vector database. So there are there's a lot of progress in improving the knowledge stores that are connected to LLMs by kind of injecting metadata into the vectors that you embed so that you're able to kind of combine standard queries with vector search. So there are a lot of developments like that, and I actually do expect that we'll have probably like a knowledge graph version of vector stores where it's a combination of like metadata or like associations between your knowledge vectors that get encoded into a knowledge graph, because there's so much information outside of just what's in the text that I think can form a knowledge graph and make it much cheaper and like much more accurate when we try to do retrieval by using all the information that's available instead of just looking at vector similarities. Yeah, but I think that's a really good question. I wouldn't be surprised if we saw something like that tomorrow, or someone's like, hey, here's a vector search implemented on top of GraphQL, and you can use this API to construct your own knowledge graphs that sit on top of your vector embeddings. Or that might exist already. So I do think it's a very compelling use case. Okay, great. Thanks for again, everyone. I'm really happy to have gotten the chance to present, and hope our community team will engage with you all later.
Thank you so much, Liam. Given how fast the space is moving, it'll be interesting to see, what you'll present about at the next ML at Scale event. I'm sure it'll be something entirely different. Thanks so much for your time. And for those that want to get in touch with Liam, really easy to do so on the community Slack, or we can share Liam's email afterwards. But yeah, just wanted to thank you again, Liam. Appreciate it.
No problem. Okay, bye, everyone.
Okay, so with that, that's our final session for ML at Scale. So we just wanted to thank you all for attending our first hosted conference. I think I speak for the whole open source community team when I say that this won't be our last event. We look forward to hearing your feedback. You'll get a survey through Hopin later tonight. We'd love to hear your thoughts on what our next event should include. This Hopin webpage will stay open for a few, probably another 10-15 minutes. Afterwards, the easiest way to get in touch with us is on the community Slack. If you want to reach out to any of our speakers, same policy. We're always available on Slack, and we'll put the link for that on the reception page. Over the next few weeks, you'll see the recordings from all the ML at Scale talks on our YouTube channel. They'll be available on Hopin for a little bit longer, like I mentioned. So again, with that, thank you all so much for making our very first ML at Scale event a success, and we look forward to seeing you all again very soon. Bye-bye.